armas loodushariduse sõber, kes sa täna oled siia majja kogunenud. Ja mul on tõeliselt hea meel, et olete tegelikult tunnistajaks ühe väga olulisele ja suurele sammule Pärnu linna, Pärnu maakonna, tegelikult suures pildis terve Eesti jaoks. Väike sissejuhatus, kuhu te täna sattunud olete, et aasta tagasi genereerisime sellise mõtteotsuse, et me vajaksime endale juurde väikest lisamiši ja mõtet, kuhu suunas oma loodushariduskeskustega suunduma hakata. Ja kõik need olulised nüansid, mis mõjutavad tegelikult meid ümberringi. Ja kliimaharidus kindlasti üks nendest tuleviku teemadest on teema, mis ei jää meid mitte kedagi puutumata. Ja nii sündis selline tore projekt nagu Nova Smart Park Pärnusse ja selle projekti tulemusena täna me tegeleme siin teiega koos just ainult selle hariduse andmise ja kliimahariduse fookusega. Selle projekti enda raames aga sünnib tegelikult loodusmaja hoovialale päris palju. Et praegu oleme poolel teel sellega, et hakata minema hankesse meie väliõppeklassiga, mis saab olema meie kliimahariduse andmise süda. Me oleme valmis saanud elektriprojektid, mis hakkavad ühendama tuule- ja päikeseenergiat omavahel ja püüame jõuda selleni, et kogu meie näitmisala suudaksime katta just selle rohelise taastuva energiaga. Ja miks see on oluline ka linnaruumi jaoks ja ka Pärnu linna ametnike jaoks ja ka teistele, et me suudaksime tuua välja just seda osa, mida on väga raske mõõta, ka tavainimesele selgeks teha, et kuidas see energia liigub, kui palju me päriselt siin Põhjamaades suudame toota, kui palju me suudame seda ise teha, kui palju me peame seda tegelikult ikkagi juurde ostma ja milline roll meil selles on ja milliseid tarku otsuseid ja valikuid üldse tegema hakata. Ja selline pehme osa kogu selles toredas projektis ongi suund selle kliimahariduse andmisele meie õpilastele ja teha seda Pärnu linna mõistes ühtse õppekava alusel. Ehk selle projekti selline suur pilt on, et me peaksime jõudma sellistele ühistele põhimõtetele, arusaamadele, kuidas me lasteaiast kuni selle kooli lõpuni seda last väga rahulikult, sellisel rahulikul moel, mitte hirmutaval ega stressi tekitaval, vaid mõistmist ja arusaamist pakkuvalt suudame peegeldada seda, et mida ta saab oma eluteele kaasa võtta ja kuidas kujundada neid loomulikke ja lihtsaid harjumusi, kus me igaüks oma sammudega oleme selle teel ääretult olulised osalised. Ja nii juhtuski, et kui me maailmas ringi vaatasime, et mida sellel teemal tehtud on ja kust me võiksime saada juba tegelikult kogu maailma tarkustest, ega me ju midagi ei pea selles mõttes päris nullist ju hakkama leiutama, kui nende teemadega tegelikult räägitud juba ju mitte aastaid, vaid juba aastakümneid, siis see viis meid kokku sellise toreda organisatsiooniga nagu see MEIE ja nende poolt välja antud kliimahariduse käsiraamat õpetajatele. Ja sellega lähemalt tutvust tehes jõudsime selle veendumuseni, et me suudame seda kohendada täpselt sellisesse võtmesse, et sellest võiks saada väga hea abiline meie haridusmaastikul õpetajatele keerulise teema käsitlemisel. Ja see on selles mõttes kogu selle olulise koolituse üks oluline punkt, mis me täna siin oleme, et õpetaja käsiraamat on täna juba läbinud tõlke, on teadlaste lugemise laua peal, et kõik ikkagi oleks õige ja kohane ja mõisted vettpidavad ja ütleme, et ka nendele pusimist, et ega tänases päevas ei olegi meil väga paljudes mõistetes omavahel kokku lepitud, kuidas me mingeid asju selles kontekstis haridusmaastikul tulevikku vaatavalt nimetama hakkame. Nii et teekond on põnev, loodan, et me oleme sellised esimesed pioneerid eriliste oluliste materjalidega ja me veame selle kenasti välja ja alati saab sinna juurde järjest paremini. Et ma tean, et paralleelselt meiega loome ju uusi materjale juurde ka siis erinevad Tartu Ülikooli, Tallinna Ülikooli teadlaste võrgustikud. Nii et teeme tihedalt üksteist koostööd ja loodame, et see kõik, mis sündima hakkab, on meie tulevikuhariduse vääriline ja teie need väga olulised sõnumi kandis. Ja eriti hea meel on meil see, et selle õpetajaraamatu või käsiraamatu väljaandmise koostöös on meil saanud siis väga hea partner Simon, kes täna on meil ka siis täna ja homme 2 pikka päeva koolitamas ja nende jaoks oli just ääretult oluline osa see, et nad saaksid peegeldada teile seda, millises võtmes, kuidas, miks on nad selle materjali just sellisel viisil kokku pannud, mida hakkavad sisaldama need ja mida sisaldavad need õpetaja tööraamatu töölehed ja materjalid, mis siis hakkavad ilmavõrgus tegema. Ja tema tänane sõnum siis on teile anda nii praktilisi väärtusi kui teoreetilisi teadmisi, kuidas nemad siis selle teemaga tegelevad. Ma soovin teile 2 väga sisukat päeva, et päris uues teemas mulle tundub, et ega me igapäevaselt sellele niimoodi ei mõtle. Ma loodan, et Simonil on väga head tööriistad, kuidas nendel on õnnestunud seda teemat siis oma kooli õpilasteni viia läbi nende vahendite, mis meie kasutusse olema saavad. Ja loodetavasti leiab siis ilmavalgust raamat juba augustikuus. Nii et kõik, kes täna siin koolitusel on ja teisedki Pärnu linna ja maakonna loodusainete õpetajad saavad kõik ka siis selle paberkonti endale selle õpetaja tööraamatu raamatuna. Aga hiljem siis kätte saada meie kodulehekülje peal. Nii et tehke ennast kindlasti meie Facebooki sõbraks ja otsige üles kodulehekülg nova.ee/part, et seal saab olema siis ka kogu selle kliimahariduse materjalide kodu, kus te hiljem siis kõik enda käsutusse saate ja roheliselt neid siis ka siis tarbida, ilma et te siis neid tehtike muul viisil seal siis paberkandjaga kandma. Aga mõned need siis ka aastame raamatud, nii et saab olema ka päris asi paris käes voodis õhtul. Nii et aga mina ütlen teile ilusat päeva ja welcome Simon, the stage is yours.
Thank you. Thank you very much.
Enjoy the day.
Thank you.
I will get back.
Okay. See you very soon. Yeah. Thank you. Thank you. Well, hello everyone. I'm Simon Klein and I work for the Office for Climate Education. And thanks to the team here, I'm here to do like this workshop with you for 2 days. And first thing, let me know if I speak too fast, not loud enough, or not clear enough, because I don't speak Estonian, I speak French or English, Spanish or German. But I'll stick to English. I'll try not to do the small Estonian I learned, just hello and thank you. I forgot it already. But yeah, I'm very happy to see that book here. That was my little baby, the first one that we published 2 years ago. So that's why from the team I've been asked to come, and I'm very, very happy. Because I kind of talk a bit about the book, but then I think the more important is that we all together work on how can we teach climate change in school. So that's the purpose. How can we, adapt and teach the topic, which is quite complex, quite very important, but also can be quite generates some anxiety. So I choose to work on some very basic topics about climate change and then to develop tomorrow more specific aspects. And I'm going to talk a bit more about the program in a minute, but first let me just introduce to you the organization I work for. If I can... It doesn't work anymore. Apple TV too, it's good. That works. Here we are. So I've got some slides, and the first ever rule is that at any time, if you've got any question or any remarks, just please do, because we are a small group, and the idea is that I don't talk all the time. But also, you'll see, you're going to have to work and talk together very, very soon. Well, what is the Office for Climate Education? I'll move here, I've got a little device here. Just to introduce to you a bit of the context of how it was created. So it was created like 4 or 5 years ago already, in 2018, in Paris, and it was created after a context of international, concerns about climate change. Of course, you're all aware, I guess, of all of the COPs, the different COPs and the IPCC reports and so on. And since like some years, every year there is this like international discussion about climate change and how can we, collectively handle it. And in 2015, in Paris, there was like the Paris Agreement of the COP21, and during that COP, they like listed some articles about how can we, tackle climate change to keep under 2 degrees at the end of the century. So that's the goal of the Paris Agreement. One of the articles is about education. How come the parties who signed up the Paris Agreement, which is almost all the countries in the world, except that the US took back when Trump was elected, but then they are back in the Paris Agreement. But they all agreed on using education as a lever, a very big tool for adaptation and mitigation for climate change. So there is this international context of enhancing climate change education in the world. And we will see it's not that easy, and it's not that simple, because in a lot of countries, climate change is not introduced in the curricula, same in France, and so we see a lot of efforts everywhere on the planet to introduce more and more of that topic in the classroom. But it's also normal that it's not introduced yet, because it's very, very fresh, new, and I think, science topic. And when I was in high school, we didn't talk about climate change, and I was in high school 15 years ago already. So things are moving very fast, but still we need to make them move faster, let's say. So the OCE, which stands for Office for Climate Education, is sheltered by 2 organizations. UNESCO is this big international organization about culture and education, and we are what we call a Category 2 center. So we're not placed at the UNESCO building and so on, but we've got this kind of international recognition thanks to UNESCO. And we are under another French foundation, which is the La Main à la Pâte, which is a old foundation, it's 30 years now, which is targeting science, every type of science, STEM, so science, mathematics, physics, and so on, to provide to primary school teachers and middle school teachers with some activity, books and activities to teach science in that level. So we heritage from their expertise, but we took it on a more international level. So we work mainly in English, but we're based in Paris, and we're very close to IPCC members. So the IPCC is an international panel on climate change, working every year. They release every other years big reports. There are international reports of the state of art of what we know about climate change in the literature. And we work very closely with them, and we are in their office. We work at Sorbonne University, where we've got a big climate change, people working on modelization of climate change and so on. And the missions of the OCE are various, but they all have the same goal, is to empower teachers by different ways to teach climate change. Yes?
These slides, are they available?
Yes, of course. No, you have to pay for it, but no. I'm joking. So we target primary and secondary schools, and mainly primary and middle schools. Also because we work in some countries, or we work with people in some countries where primary and middle schools are mandatory, but after there is a drop in the classroom, so it's interesting to work with where there are more students. And also because in our country there is not much done yet in the curricula for those levels. So say from 8 years old till 15 years old, that's our target in terms of when we work on new material. The idea is to work in different countries, and you see the percentage, but we don't really do that much also because of COVID and so on, but we start to do more and more international partnerships. We've got a big partnership in Latin America. We've got another one coming in Africa with 3 countries already. And the idea is for those partnerships is more to work with local organizations, with local governments to do some teacher training, capacitation, and so it's less that we go and we do, but it's more like we do collaboration and cooperation. We do a lot of professional development. It's a bit what we're going to do for 2 days. And I do that a lot in France. We do a lot of online training as well. We developed a MOOC in English. So a MOOC specifically on how to teach climate change. Because there are already quite a lot of MOOCs available on what is climate change. So the idea is more to work on the pedagogy on that MOOC. So I can send to you as well the link of the MOOC. And we do a lot of production of resources, and that's one of the examples of a book we do. And finally, that's a bit of a new missions kind of thing. We do quite a few support to public policies, and mainly we work with policies when they want to change their program and curriculum. And so we help them out to do that. And I do a bit of research in science, so it's a side project of research action. So we do develop programs, and then we test them in classrooms, and I do a bit of interviews with students and so on to validate our material, but also to help out the research in climate change education. So yeah, that's our big words, active learning, interdisciplinary. Yeah, so the main aspects as well, and we were discussing a bit that before, is that we work in a way of, we don't target specifically one discipline. At least in France, we've got in middle school biology, and then chemistry, and then French, and they're all separated. But the idea is that for teaching climate change, we need interdisciplinary, and we need teachers to cooperate together, and disciplines to be merged. So that's a dream, let's say. And also because we know that climate change is not a topic that is exclusively science topic. Because it's more than science. It's science also how society is dealing with climate change, and that comes into other aspects of teaching, right? It comes to literature, it comes to arts, it comes to any type of teaching. So that's why in the book we try to introduce more different topics than just science. Even so, science is the basics, and today we're going to do a lot of science. Tomorrow a bit less. But just to let you know that, the idea at some point is try to merge when science is meeting other disciplines and what does it, come from. And what we call active learning pedagogies is the way we do our, the main, especially for the science part, we do a lot of active learnings and inquiry-based pedagogy. So today we're going to do inquiry-based pedagogy, and we're going to reflect a bit on it at the end. So the idea is to put the students into the process of, making out the knowledge by questioning, testing, and then validating the hypotheses and so on. So we're going to do a bit of that. And yeah, so the goal is to empower teachers so they're able to teach about climate change. It's a big goal, and sometimes a missed goal, but sometimes useful, sometimes less useful. But there is an international recognition of the needs for this type of activity that we do. Is that when you look at different reports, and UNESCO is doing a lot of reports on in any countries where does climate change stand in the curricula, for instance, and we see that for, I think they studied 115 countries, something like that, and they found out that in the majority of them, there are like either no focus on climate change or very minimal, like, you know, all in all is like 87% of the curricula they studied were like almost nothing. Then minimal, and they qualified moderate, something where they found, you know, like occurrences of the word greenhouse or stuff like that, and it's only 2%. So there's still like, you know, work to be done, but the fact that people are studying that, you know, show that there is like a movement coming up, right? And there are like a lot of, you know, obstacles of having such, you know, ambitious climate change education, because the main aspect, I think, for me is like the complex subject. Climate change is a very complex subject. It's a large scale and long terms, meaning that what like consequences we have now have like consequences in the future and so on. But they also need like kind of like innovative pedagogy or like new way of approaching the topic. I mean, we can do like basic science, but I think we need more, and that's what we're gonna like discuss today, I think. And this aspect of emotional, how to deal with eco-anxieties, for instance, and we're gonna work a bit on that tomorrow. Okay? So I'm gonna keep that for tomorrow, and yeah. So So I won't go into that process unless you're interested, but we can go back to that tomorrow if you want at the end. The way of like how we work on writing that specific book. I think it's interesting once we, you know, go through it, so I might keep that for tomorrow, but that's just a short presentation of the material we produce. They're all online, they're all available in 3 different languages for free, French, English, and Spanish, and now one will be also available in Estonian pretty soon, thanks to you, so that's this one. KLIIMA muutus jama. In English, climate change and land. And so that's the one I produced when I arrived in the Office for Climate Education 3 years ago. Before that, I was, I forgot to say, before working at OCE, I used to work as a researcher in ecology, and I was working with bees, with honeybees and bumblebees. Yeah, so I switched to education and science dissemination, but I still love bees and I still do a lot of stuff with them, and yeah, and that's why also I work on a specific subject about the land for ecology. I mean the link between ecology and climate change, and that's why I'm very happy to be here as well. And the one who was published when I arrived is more focusing on ocean and cryosphere, and my colleague who left now, but she is a former glaciologist, so she was very like, you know, closer to the topic. And that one is more about, related more about like the cryosphere, all the sea ice and the ice and the biodiversity in the ocean. But then we've got also those like, we call it summaries for teachers. So as you may know, the IPCC is producing a lot of very big books of like what the state of art of research on climate change. But they also do a very small one, which is aiming for policymakers, which is called the Summary of the IPCC Report for policymakers. And we do the same one, but for teachers. So we've got like an agreement with the IPCC, and we do that. So we did one for land, we did one for ocean and cryosphere. And then we also have those protocol for professional development. So today we're going to work on one, which is how can we understand greenhouse, and we've got like a paper to show how, as a teacher trainer, for instance, or someone who wants to, you know, like disseminate this type of pedagogy, you can also use that type of resource. And finally, we've got some online material. I'm going to show you some today or tomorrow that are also like in the 3 different languages, also German, and like for free and so on. And they are they're linked to like activities in the book and so on. So that's for. Yeah, I won't go into detail on that. We're going to have time to go back to it later. All right, and that's one last thing I wanted to tell you, and I think that's the main message actually. the book is done in 2 parts. So, I don't know if you've got here. Yeah. So, there's like a first part, which is more like, actually 3 parts. First part is more like a scientific and pedagogical background for the teachers, to have like, more like basic knowledge and so on, and to go further into the science and the pedagogy that is behind the book. And then there is like turnkey activities for teachers to, like do in the classroom with the different material, the documents are needed. And last part is we act. So it's a detailed project or ideas, and the idea is always to link both. And the way we think about it is more like, okay, if you're like a school, like a middle school, like a primary school, maybe you can choose like 3 or 4 activities you can do in classrooms, but very like soon in the school year, put all your school into like a real project for the students to be like active and to be in that process of being in the action, like towards like a better pro-environmental habits and to have like a real impact, and that's very important. And that's why on top of the book, that's an idea that we developed, and we test that idea now in different middle schools in France, and I'm doing some research on those middle schools. If the students, for instance, who are following this path are more able to understand, but also more able to cope with eco-anxiety and more eager to act towards pro-environmental behavior. And so it's like a different path, different steps, kind of like a path all around one school year. So it's like a 1-year aspect. The first one is just about the learning. So it's a few activities that you may choose in the book, mainly focusing on the basics of climate change. And then you've got an activity looking at the emotions of climate change. How do you feel when we talk about climate change? We're going to do tomorrow. And one about designing solutions. So brainstorming with students what they want to do. And that one goes, let's say, just before Christmas, and then you've got the rest of the year to actually do one big project. So that can be different example here. We've got acting together, which is either individual actions that they can do in the family time or in the school, or we can do what we call a KLIIMA-thon. So KLIIMA-thon is more of a project-based pedagogy where you've got one day of full day about climate change, but on a topic that is related to the school context. Say we had one in France regarding urban heat island. So it was in a city where you've got no vegetation at all. It's very mineral, and therefore during the heat season, during heat waves, it's very, very warm, and it's very hard to go to school. So the students, and with some partners and the teachers invited some like local representatives, but also scientists and so on. Students like learn about the topic for the full day, and at the end of the day, in groups, they decided different project they wanted to do, and then they elected the best project they wanted to do. So at the end, they elected a project of a contest in the neighborhood of like vegetalization, so like small gardens, but also in the buildings to have like flowers in the windows and so on, and they went with like social media and so on to activate this context with the local neighbors. And the results was actually to have a greener area. So it all came from the students during that specific day, and then it followed all the year long. So the idea is with this type of path is to have like different aspects of pedagogy that link the students into I understand, I feel, but also I go into action. And another path that we may use is imagining hopeful futures, so more like creativity and how do they project themselves in the future. So that's, that part is less stable for the moment. We don't have like that much material, but we're testing that. We've got like a grand project to test more. Okay, enough talking for me. If you got any questions on that, just let me know, and then we can switch to more practical work. Is that right? Good? And Norway is going to send you all the material. Okay. So let's talk a bit. And now you're going to work a bit. Let me try this works.
Talking about using
Again? Sorry, I'm just like manipulating my computer.
How much do you experience across, say, teachers do lessons outside activity?
Yeah, it's a new, well, since COVID, mainly, there is this like, big movement towards outdoor education, which is growing up in France. Actually, there is the first international conference about outdoor education sitting down next month, or at the end of the month in France. Yeah. They claim it's international, but in the program, I didn't see anything that was not like, France. But yeah, no, it's interesting, and I think it's very, there's a lot of values in it, and I think that's, the way we should do it. But somehow, in that conference at least, there are some I don't know, it's not all science-based. Sometimes it's more like almost esoteric, or almost like connecting with nature and so on. That is far away from the importance of a science-based education, or at least for climate change. I mean, it has to be based on science at some point, but there are high values, obviously, on that topic. And I was doing it last week. I went to do some stuff about bees. They got a show about bees, like a conference show. And I was doing some middle school and primary school, and we did an outdoor education for the full day. And it was crazy how the students, according to the teachers, were very into it. Even so, the one who were not into science, in the classroom, there's this yeah.
The lessons outside.
I think it's very.
Different. Because I think Estonian students, the studies have shown that in this country we don't, because we don't have big floods, we don't have big droughts, we don't have earthquakes. Youngsters sort of think that everything's fine.
Yeah, right.
We don't have climate change.
Yeah.
It's a very controversial thing that they only see from social media that somebody's, this young girl is screaming and chaining herself up and talking about climate change, but we don't, because we don't actually feel it and see it, the awareness of it is just very, very low. And that's very good.
Yeah. No, I think it's very interesting, and that's why we can discuss that a bit further, because we all have our own perspectives, and in France, stuff are moving fast, especially in cities, because of we are a country with Spain and Portugal, who are hidden up by heat waves quite dramatically.
And big fires. And
Yeah.
It's amazing how we here, we're very happy when it's a hot summer.
No, that thing. And I was saying, when I arrived, wow, that's very nice summer and very nice weather here. I didn't know that it was unusual for the season. It's actually hotter and warmer than in France right now here, which is why I'm very happy. But,
there's a study been made by Estonian youth organisation.
Okay.
And 84.2% youngsters who were questioned don't know anything where they can participate in order to speak their mind or act towards helping about the climate change. We don't know this. There's the same study, but there's another percentage brought out where there's no material. This is a very big material.
Yeah, that's very interesting, because it relates to, the teachers are claiming the same thing in the UNESCO study. They're actually showing it's not only I just showed you that they looked at the programs and the curricula. Also, they interviewed some teachers, and they're all saying yes, we want to teach climate change, but we're afraid to do it because we don't know, we're not we don't have the you know, like the knowledge.
Yes.
And there is this very, and it's also very common in France compared to other countries, especially in the US. In France, there is this like tendency, especially in primary school, we don't know, therefore we won't do it because we're afraid of, we don't feel legitimate to teach climate change.
Yes, yes.
Which I think is a kind of like a mistake, because we all are legitimate to do it since we just, you know, learn about it. But then, to learn about it, we need material, we need like teacher training, we need like, you know, capacity building. So that's why I'm happy you are here, but also that, yeah, that's a very nice approach. And also what you were saying, that youth are like, they want to do stuff, and that's something as well. It's coming up in the studies, but it's not clear yet. I think there is a mix for young students, especially in the teenagehood, where they're either bored because we don't teach a lot about climate change, or it's, you know, starting like a other, you know, running topic, and they kind of like are bored about it. And I've been seeing a lot of like students who are like, yeah, well, I don't want to learn more about it. I want to act. I want to do. I want to make difference. So there's this like
because they're
demand.
going to live in it.
Exactly.
We're going to die.
Yeah.
We don't care. 50 years, we're not going to be here.
I know, but then...
It's up to you.
Yeah. That's why it's interesting. I think that the position of a teacher is very special in that sense, because in a way, and it's very hard, you are with your students, developing that knowledge together, and then you have to answer that big demand of them being, I want to do stuff, I'm worried about it, what can we do? And then I think one of the best options in my mind would be, well, yes, you know what, I'm not a teacher anymore and you're not a student anymore, we're all like citizens, and therefore, let's try to make a difference together. And that's where like acting, like, you know, putting your classroom to action and so on is very important. But then it's very hard because like the teacher in his shoulders is like holding all of that. Yeah, and also one of the, I mean, eco-anxiety or anxiety by the students is one thing, but then promising them that you're going to make a difference, but then don't following up the project because of a lot of reasons about we don't have the money, we don't have the time, and all the reasons we know as grown-up are hard to accept for a young citizen in becoming, right? And therefore, deception is part of a big, you know, psychological intake in comparison to eco-anxiety. So it's very, yeah, it's very interesting. And to finish up on, they are looking for like places and action to do. In Paris, there is like a building that is called the Climate Academy, Académie du Climat, which opened like just right after COVID, just before COVID happened. And the purpose of it is actually to gather youth association and to do some teacher, like the young training and so on. And the idea is a bit to be a hub for the youth who want to be engaged into action. I'm working a bit with them. It's not that easy to make it work, but I think it's a nice thing. So that can be this kind of like, you know, places where it's identified as the places where you can go for like seeing conferences, go to do some workshop, but also meet people and engage together. And it was actually the MEIE of Paris who just built that up. So it's also political, which is sometimes not. Yeah. All right. Let's move on. So this is a video. I'm going to put it more, but you see here that's the map. Estonia should be always where it is, somewhere here, right? Okay, right. And you see different colors, right? From blue to red-ish. And the colors are actually what we call like temperature anomaly. So there's a difference in temperature compared to an average. The average is the 70s, so like between 60 and 70s of this century. So it's the average was like, okay, we take 0 in the middle of the 70s, and now we see, is it colder or therefore it's blue, or is it hotter year after year than the average? You see here the years are like going up. So we're going to hit pretty soon the average time. So the average is done like from an average of everywhere on the planet, on the surface of land, also ocean. That's So you see now we're hitting 2000. Okay, now what do you see? Yeah? In what form? It's hotter. Why? Where? North part of Earth, yeah? It's hotter north part of Earth. What else?
In the Arctics.
In the Arctics? Uh-oh. Why is it hotter northern hemisphere? You know?
It's more land.
Yeah. And why therefore?
The ocean moves all the time,
Yes.
so it's different, the heat.
Yeah, that's because of the what we call thermal line circulation, which regulates the heat. The energy is like regulated in the ocean, but also it's the water itself has like a lower thermal inertia, so the fact that it can gather more heat energy and it doesn't, warm as much as the land. So like the two reasons. What else do you see? Which is quite obvious, but also it's very interesting and important to say to students.
Actually, it's heating up all over, not just northern hemisphere, but everywhere.
Yes, it's hitting everywhere where it's like all orange. But you say it's like warmer here. You see that it's not linear. It's not like as warm everywhere. So there's like a lot of heterogeneity, and that concept of heterogeneity, it's hard to say, is very important as well, because the impact of climate change are very heterogeneous, and the provision and the uncertainty is very high. So if we look at the map like that and we understand, okay, even so we talk about degrees of increase, they always average degrees, and when we say, okay, it's like in average this year is 1 degree more than like 15 years ago, what does that mean? It's important for like any young or even adults to recognize that it's not homogeneous, and you've got huge variability in where it's warmer or not. We've got an answer about land and ocean. Also, as I was saying, majority of the figures we use when we talk about climate change are always average of land and climate, and they don't follow the same path. So that's when we take out and we separate land from global temperature. You see global temperature, we've got obviously an increase, so that's again anomaly between 0, that anomaly is like from an average that was before, so an average about before what we call the industrial revolution. You see like a constant growing up with like in the 70s, like the steep is like higher, but what you can see as well is that we've got more and more like a difference between global temperature and land temperature. So basically here we've got land and ocean, and here you've got only land. And usually we talk about global temperature by a mix of land and ocean. So it's interesting as well to have a look at what does it look like in average when we only talk about land. And you see that it's higher. And also the difference that we see in different regions, it's explained by land, but also explained by all of the atmospheric currents and the local areas and the local geography. So basically, if you're like closer to the sea, you may have like a less hot weather because you've got like this sea protection, like the buffer effect from the water. But then if you're inland, you may have more chances to have like a higher and longer heat waves than by the sea. But also you've got like more complex and scientists don't really know yet, and there's like more and more projects on modeling very finely the movement of the mix of ocean and the atmosphere. And there are like so many interesting but very unrevealed yet interactions, especially in those zones, like intertropical zones, where you've got like evaporation, which is very high, but then all of the water cycle, which is disturbed by climate change, that may introduce some drought in one part, but then huge inundation in other parts, and that's what's happening at the moment as well. So even so, we can't tell everything from this video. I think it's a very good one to explain that heterogeneity, and then to go more about like, okay, land versus water. And we can do a small experiment on it, which is in our first book. We just place water and a thermometer, and then you put some rice or semolina or sand to represent the land, and then you just take temperature, you put that under a lamp, take temperature, and you see that in the water it doesn't increase as much as in the land. So you can go in that path, and then you can go in the path of like heterogeneity in the water cycle. Okay, so the consequences, what consequences do you think what we saw before can have, or already have? I think we discussed it already.
The permafrost is melting away?
Yes, that's very close to you, right? Because do you in Estonia have permafrost or not?
No.
It's more like northern.
No permafrost.
Yeah. Yes. What else?
Different spaces are changing.
Yes, we talked a bit already. There's like a lot of migrations of species, and therefore some disturbance in local ecosystems with invasive species coming because of migration, and also that topic is quite unclear sometimes because some species are very easier to move than others, and there's some drivers in the species themselves that make some very able to colonize other territory, and some other are not able to do it. So there are a lot of movement in that space. What else?
Sea level.
Yeah, where does that come from?
Ice is melting.
Yeah, which ice?
Nothing.
Yes, every ice.
Yeah, imagine all those rich people who are building their nice summer houses right next to the beach. In 20 years, it's all going to be underwater. Or 50 years, maybe. What a waste of money.
Yeah, that's true. Well, that's true. I don't know for the rich people, but yeah, it's true that.
I live in the area where it's so dry throughout the summer now that I don't have any water in my well in the middle of July.
Yeah.
I've lived back in Estonia for 6 years. Last year, I was at that Rondon's rustic head because the water was so bad, I couldn't play earth, the land. Seriously, there's no water.
The droughts.
The rain, yeah, the west side of the coast, the west side of the coast, we hardly get any rain. It's really dry.
Yeah. That's also local
It's
aspects.
probably a minor thing, but I see it, the difference. In 6 years, I see the difference. So,
But that's the thing we were talking before. It's the complexity also comes with the time scale, and 6 years is not much, but for a young, teenager or something, 6 years is a long time. So that's where also complexity is hard, to get. We won't go into detail of we will go into detail more about the consequences later. But according to you, what is the main driver of that change in the global temperature? that we see since the century. Yeah. Greenhouse gases. And the phenomenon is therefore the greenhouse phenomenon, right? Yeah. Is that a natural phenomenon or like induced by humans with green?
By humans, yes.
Yes? So if there are no humans, there will not be any greenhouse effect.
There was minimal, but not as much.
Yeah. Yes, we're going to see that later, but...
There's only so many cows that can poop.
Yes, I mean the greenhouse effect is a natural phenomenon, but what we see now as a global warming, and what we call global warming and climate change, is the fact that this natural greenhouse effect is, changed by human activities, by the releasing of different greenhouse gases. And now, that's where you're going to have to work more. Oh yeah, so you talk about it, just a small historical and methodological point. The greenhouse gases have been identified, mainly CO2, through different methodology, and the one that just stood by some solid stone into the link between CO2 and after that all the greenhouse gases and the increase of temperature is this kind of studies. So that study has been done by Jean Jouzel and other collaborators, and they went down to the South Pole in Antarctica, where in Dome Sea, you can see here, it's like an international study station, research station, and they do what we call ice carroting. So they just took out some carrots in the ice, and they can see in the ice and have a look at the bubbles of the atmosphere that was trapped in the little drops of water that have been, first it was gases and then water and then ice, and they've been packed into those kilometers of ice in the core of Antarctica. And when they look at it, they can do two very interesting stuff, or three interesting stuff. They can have an ID, approximation of the date of when this atmosphere has been trapped, the approximation of the temperature around, and the approximation of the concentration of CO2 in the atmosphere. And then you can do draw some graphs, and you see here that's the atmospheric concentration, and you see changes and so on, and that's years ago, 1,000 years ago, so 800,000 years ago is the oldest record we can have in that CO2 levels in the atmosphere, which is quite far away in the past. And then you can have the Antarctic temperature in terms of changes according to, again, a average, which might be always the same, like early century. And you see for changes, big changes, right? Temperatures has changed in the past very drastically from -8 till almost 4. And but you see that those changes, even though they look quite fast in that graph, when you look at the scale, it's very long, because the changes from here to here is what 100,000 years, which is a lot of evolution in species. Evolution also in the land, thanks to tectonic plates and so on. So it's quite a long time, but still you've got variation in the climate. And then if you put the atmospheric concentration of CO2 in regards, you can see that the pattern is very, very similar. It's so similar that it's shocking. And they were quite shocked when they saw that, because they were like, oh wow, there is something there. So that's the first kind of explanation of, okay, global temperature is linked to gases in the atmosphere, like CO2. And then they look at those gases in laboratory with some spectrography and so on, and they found out that those gases are able to trap heat. We're going to see that later, but that was a demonstration for observation, and then they did some analysis in laboratory, and now we do more and more modelization to have a clearer idea and also to continue the story. But then what you can see here, and you could have a focus on it, but we've got a very steep and unprecedented, like there were never ever a long and big, very steep peak of CO2 in the atmosphere. That will be followed by a temperature change as well. There's a small delay anyways, but the quite interesting remark from this graph is the time scale. Yes, climate changed a lot in the past, and when we talk about climate change, we can talk about like paleo climate change, and to be accurate, we should say like current climate change, right? But the current climate change, even so, already in the past we had like changes and big changes in the climate and the planet. This one actually is caused by human activities, but also is going very, very faster than the one previously. So like obviously all of the nature survived and or changed, and that's normal through those variation of climate in the past, and they will survive and they will change even with this climate change that we see now, current climate change due to human activities. But the question is more about how as humans we can live in that space, and how can we do to minimize the impact of this climate change. That's what we're going to later on. But I want you to kind of focus more on that story about the greenhouse effect, what's going on there. And to do that, I'm going to ask you in groups to make a comprehensive drawing of why climate is changing. And you can focus on that aspect of the greenhouse effect, for instance. And the idea is just to have a drawing that you can, how would you explain it to students? With a simple drawing, with some arrows, with some explanation and so on. So we want to focus on the physical aspects of it. We don't want to focus more on the implication for human activities or what kind of human activities are causing what. So it's more about the greenhouse effect, all the effects that might be in place when we think about surface, when we think about sea ice and so on. And then you're going to present it to the other groups.
Ma võin kollast juurde tuua. Kollast väikest. We don't have yellow for this one.
Oh, okay. You can make a...
Anneli.
Well, you can make like other colors. It doesn't really matter.
Kollast tuleb juurde, Anneli toob.
Okay, so you got like 10 to 15 minutes, and then you present to each other. It doesn't really matter if it's not finished or perfect. It's more of going for like discussion.
Kus see pruun jäi? Ja pruuni tõi ja siis see lood huvitust, me
mul on sari. Aga võib-olla. Ma teen väikse kiire ja siis läbi teha, näiteks teen 2 piirme läbi, võib-olla midagi niimoodi.
Don't forget that we want to focus on the greenhouse effect, or like how can we explain it with like arrows and so on. And for instance, the interaction with the sun energy and the atmosphere and all of that.
juba tegelevad.
no seda võib tegelikult rääkida. Okei.
Okay, 2 more minutes. Okay, so even if you're not finished, I think we can present your drawings to each other. Who wants to start? Yes? All right, so please, we've got one first group here. You can do it in Estonian or in English.
I will try to do it in English.
Yes, perfect.
Okay, wait.
All right, can you all see?
Okay, we try to do a very simple explanation of why the climate is changing. The greenhouse gases, basically how they, why they stop the Earth cooling down, essentially.
Yes.
Yeah.
Yes.
Okay.
So sorry, what? Okay, yeah. I'll do it.
Okay. On the top, we have the sun. Below that, we have the atmosphere. The atmosphere has been saturated by CO2, essentially, and the CO2 doesn't let the sun rays, which are reflected from the surface of the Earth, they can't escape through the atmosphere because the CO2. Some of it bounces back to the Earth.
Where does? Can you show me where it comes back?
Sun rays are here, and we did 2 lines because some of it still manages to escape, but not all of it. The majority of it still like bounces around here, essentially.
So the yellow, why is it stopped here, but here it's not stopped? And what is the difference between the yellow and the purple?
The purple is essentially the heat of the Earth itself as well, because it can't escape all of it. It's basically the CO2 in the atmosphere holds it. That's why it's the greenhouse gas.
Yes.
Essentially, it's a greenhouse.
Yeah.
You have basically a see-through ceiling. The heat can't escape it. Some of the heat can, but majority it can't.
Yes, so the heat that is here, purple, a bit can go out and a bit can't.
Yeah.
But then, what is the yellow one? Is it heat?
It's the sun rays.
Okay.
I know it's basically the same thing.
Yes.
But it's the how do I explain it?
I know it's hard, but
that's
why we do this exercise, because you see that the word, like it's the hardest part is actually to explain granular effect. But you're doing great.
Because I mean, all of the heat isn't produced by the sun. Some of the heat is produced by the Earth itself as well, with the ecology and everything else, nature itself.
Yes.
The purple lines are the Earth's heat, and the yellow is the sun rays that come through the atmosphere.
Yes.
Some of it can escape, and some of it can't escape.
Okay.
That's why there are two lines. It's a bit messy, I know.
No, but like And so you say that the purple one, which is heat as well. Can we see that one?
We can actually. I think I can. We can. It's the heat waves, basically. I don't know.
It's waves, yeah.
But yeah.
So there are waves that are like convecting heat.
Yes.
Does anyone know how we call them?
I don't know what how to call it in English.
Yes. So maybe someone can say. Well, like translate it.
Jah, põhimõtteliselt nagu, et kui ei mitte miraaž, aga kui sul näiteks elektripliit on ka vaata, siis sa näed seda värejab niimoodi. Kuidas seda nagu nimetada, ma ei tea.
Õhk leevendab, vaata, et asfaldi kohal. Waving heat.
Waving heat.
Waving heat.
No, because heat wave is when it's too hot. We call like in English,
You can kind of see the air is wobbling above the surface.
I don't know if it's the correct thing.
No, I'm looking for something else.
Okay.
Something that we can't see, but that is actually transporting heat.
Okay.
In English, it's called infrared radiation.
Oh,
Do you know that?
okay.
So you actually, here, you draw infrared radiation. How do you call that in Estonian?
Infrapunane kiirgus.
Yes, infrared radiation.
I don't know if I meant that.
Oh, you don't know if you meant that? Okay.
Yeah, but maybe it's the correct thing.
Yeah, well, like, it looks like that.
Okay.
And actually the correct thing is actually, so you draw here. Are you alright here? You draw here like rays from the sun that we can see. They are visible rays, right? The visible ray is transporting heat, but also light, that's what you can see.
Yeah.
Okay? And then they reach the surface, right? Some of it bounces back. It's here, I'll show it.
Well,
No?
okay.
Okay?
This ray, I did only two because that's no.
No, like, yeah.
One of the rays bounces off the atmosphere to the ground as well, and maybe bounces a bit more.
Yeah.
But the second ray is here.
Yeah.
It bounces off the ground and it manages to escape. At least some of it.
Okay.
Yes.
All right. We're going to see that, but then that's not correct. This one, it can't happen. The thing is, if you got like a yellow ray here, which always in the codification of the colors and so on. That will be light, so that will be like heat that is transferred by the sun, visible light, right? So visible heat that is like that we can't see, kind of thing. So it's like the visible heat, and actually, yes, some of it is reflected by surface, and especially by very white surface, right? So if you've got like white surface, it just like has like a mirror, but not all of it. Some of it just stays in the ground, it just heats the ground up, all right? Yeah. So everything that is touched by the sun, basically, and us as well, when you go out in the sun, it's like warmer, right? You'll feel warmer, and you're warmer. Because anybody, any like structure, any like molecules, when it's heating up by the sun, gather energy, and then it just cools down. It cools down to get like a average temperature. By cooling down, it's emitting those rays that you're showing it, which is like heat that is escaping, but we can't see. That's the infrared radiation. Okay, so that's correct. That's correct. So basically, that heat that we can't see, infrared radiation, is trapped by the CO2. Okay. It's trapped, but it's not like just gathered. It's the same process as in the Earth. The CO2 gathers and then re-emit as well. So we should have other like little rays in the same color, so that we can't see, goes in up and down. So that's why we've got some that is escaping, because it's not in 2D, right? It's like 3 dimensions. So it's radiating everywhere from the CO2. So it's radiating, half of it is radiating into space, half of it is radiating down. So the bouncing back and forth is more the purple rays, the infrared rays. But otherwise good. And you've got, some of it is actually bounced back here. Do you know why? What do we have in the sky as well?
No, I don't think.
The clouds.
Oh, okay.
Yeah, the clouds are also acting like a reflecting, like a mirror as well. So part of the sun rays are actually going out. Okay?
I remember something that I forgot. Is why Earth is heating up is because there's less ice on the polar caps, and sun reflects on it, and that's why like there's less ice, so the sun rays can't reflect as much to the outside, basically. Okay,
yes.
I remember
it just it stays in the ocean or the land around it.
Yeah.
Do you know the name of that phenomenon?
I don't think so. No.
It's albedo.
Albedo?
L-B-E-D-O.
Okay.
And that's the name of this difference in radiation. So a black, when you wear a black t-shirt outside, you feel very warm compared if you wear the same fabric, the same t-shirt but in white, right? And that's just because the color blacks, or everything that is dark, is absorbing more the heat than something that is white that just reflects the heat. And therefore, if you wear something black, there is radiation around you. The radiation just, which is the invisible radiation, just goes around and stays around and then eventually leaves the atmosphere. The heat reduces slower than when it's just like heating up. And the same thing happens in the North Cap or North Pole with the sea ice that is melting. So you've got less white surface and the ocean is like way darker than the ice, right? So if you reduce the number of ice, like the area that is white through the ice, then you've got more absorption of the heat here than less. So what you can do as well, either like instead of having one simple line, you can have like a big line, and then you can express, say, that's 100% of the energy, 30% just bounce back and leave in the atmosphere, and then you've got 70% just that is heating up by the surface, and then radiation everywhere. And that's very good that you didn't place the radiation waves, that invisible light, just here, because sometimes and very often students or even teachers put it just here, meaning that it's bouncing as well, but it's not bouncing. It's more radiation, so basically the heat just gather somewhere and then just surface gather and then radiate in every direction. Okay? Okay, good. Can we move to another group? Who wants to present their work. And I see that all of your work are very complementary. That's interesting. Yes?
Yeah, it's practically to some use it. I don't know.
Here is unhealthy earth.
Yes.
Feeling very hot. And here is the main reason we have very many people. And all these very many people need to eat. That's why they are raising cattle to produce food. And that's why that's the reason of deforestation, to create more land for producing food. And of course, all these people need to drive cars and need power, electricity, and that's why there are many factories here, many cars here, and that's all.
All right. So yeah, you just presented more the causes of climate change due to human effects. And I think that's like, yeah, another type of exercise, and you present all in all there, but what can be interesting is try to have also that aspect, molecular aspects on it. So we can, do that later today, because we can explore more of that aspect today. But that's interesting. I've got a question about the cow. Very interesting cow. So it's CH4 stands for methane. Yeah. And does it come from where does it come from?
Inside the cow.
Yeah.
And also
Grass-fed.
And yeah, grassland as well. But in the cow here, actually, the majority of methane is actually going out from the mouth. It's burps rather than like farts. I mean, like 3% might be farts, but like almost like 90% is going out from the mouth. Yeah, because they are ruminants, so they kind of like eat the grass, but they can't digest the grass, and they take out all the protein that is essential for their large bodies to function. They don't eat meat, right? And the grass is not full with any protein at all. They're not like some of it, because they eat some fabaceous, for instance, they have some nitrogen from it, but the majority of their regime diet is not based on nitrogen, it's more like just carbon and carbohydrate. So there is like this, what do you call that, symbiosis with bacteria in their guts, and they've got like different guts. And the bacteria, they digest the bacteria, but the bacteria digest the grass, and by doing that they release methane as a byproduct of the fermentation of the digestion of the grass. So for the cow, the sheep, and the goats, same process, and actually, yeah, there's like a byproduct, let's say. And so they have a diet, they're not vegetarian, because at the end of the day they digest like bacteria that eat the grass. It's like a two-process digestion that appears to release some methane. In grassland as well, also in rice paddies. The rice paddies, when you like in South Asia, where you produce rice, they also release quite a lot of methane, but less. The cows are the main ones. Your turn, or anyone?
Well, we have exactly the same one.
Okay. Anything else to say?
We also have the cows. We
Yes.
did a little correction. Burps are here.
Okay, and then
Something else is here.
And so you've got methane, CO2.
Yeah, it's all about the people
Yes.
here.
And they're like small people with like
And
very
the
large
production, and
clothes.
the mining, and the bogs also.
Yes.
And the reflection also here. Something goes up and something comes down.
Okay.
And it's almost the same, yeah.
Yes.
All of the production, all of the cows, and all the mining.
So you've got CO2 a lot and CH4, and you guys had another molecule, right?
We had methane and H2O.
Yes.
Because there's some water vapor in the atmosphere as well.
And vapor, water vapor, what does it do? Why did you put water vapor in it?
Mix alcohol. Oh, okay. H2O because because a lot of processes produce water vapor, and because of the heating of the water sources as well. A lot of the lakes and so on, they produce water vapor because it heats up, goes into the atmosphere as well. Okay. 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 And the H2O is less, let's say, stable. It can degrade quickly. But CO2 can't. CO2 is more, let's say, stable.
Okay.
Okay. And H2O doesn't disturb basically the heating of the plant as much. As much. Okay. 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 And H2O doesn't. It's always there, but CO2. Okay, but CO2 is
the main one.
The main one.
Yes. So do you have it? Like, thank you. So they put HDO in their drawing on top of CO2 and CH4. And the question is, so what it's a vapor like in the atmosphere. Yes. What other gases do we have in the atmosphere? We've got HDO, CO2, methane, but the main one...
Nitrogen?
Yeah, nitrogen.
Oxygen.
And oxygen, otherwise we can't breathe. Does oxygen has an effect, has a greenhouse effect or not? No. The answer is no. I mean, if you don't know it, we can't test it, but yeah, the answer is no. H2O, oxygen, dioxygen doesn't have any effect on the greenhouse, but water vapor has an effect. It's actually the main greenhouse effect is water vapor. So water vapor has an effect on the greenhouse. It's trapping more heat than CO2, but human activity doesn't have any effect on introduce more water in the atmosphere. Actually, all of the greenhouses that are problematic, let's say, that are the ones that are increased in the atmosphere, are due to human activities because before being in the atmosphere, they were stuck in the ground, right? They were coal, they were like petrol, they were gases, and they were like stuck under the ground. And we're going to play tomorrow a game to look at the cycle of the carbon in the ground, in the atmosphere, and why do we have an increase. The water just goes from atmosphere back to the water in the ocean, and this cycle is not disturbed by human activity. There is no like underwater, there is some underwater under the ground, but it just goes very quickly back to the ocean. So there is no like, water stored in the, under the soil, in the soil for thousands of years, such as petrol and gas, which are carbon that is stuck for thousands of years in the ground. And now humans are like, getting out very, very quickly. So the water has an effect on the greenhouse and has a huge effect on the main greenhouse, natural greenhouse that we have on the planet. But then there is no effect due to human activities. But there are some suspicions at the moment that because of the heat, the atmosphere can have more water. Actually, when the temperature is higher, the gases can have less space and they're more volatile. And therefore, that's why the atmosphere that we have now, there is a bit hotter than the atmosphere before has a capacity to have more water in the atmosphere. So there is like a kind of like a positive feedback saying that because it's hotter and hotter, there is more and more water in the atmosphere, and because there is more water, there is more greenhouse effect because of the water. So there is like a, kind of like a feedback loop because of that. So yeah, just to point that out. Can we do quickly your twos?
First of all, I'd like to say thank you for my new advisors. We have collectively drawn up a picture here that is probably going to be a scene out of a horror movie. This is what you are not supposed to show students, the kids. It's supposed to scare them. Cow shit is bad somehow. It's also very good for the plants, as we know. But this is a highly anxious image of we're all going to die, which we are. And we would like to know how to teach the climate change to the kids that is prosperous in the long run.
Yeah. Well, that's a very good introduction to this 2-day workshop, even so. It won't be enough.
They told me to say that. I didn't know.
Yeah.
But it's very good. It's for me, it's very eye-opening because, yesterday I did an outside learning lesson in my school, and I asked the question from one of the graduates who's going to graduate this year, and I said, if you return to this schoolyard, we've counted all the trees, we've named all the trees in our schoolyard, and we have 94 trees in our schoolyard, in London School. And I said to one of the guys, I said, what do you think, if you return here in 50 years' time, that tree that I asked you to draw today, will this tree still be here? And we don't really know the answer to that question.
Also, like depending on the age of the student, there is something we're going to talk about later tomorrow.
He's going to be 64 years old.
Okay, so he's older. Because like for younger students, it's very hard to project. I mean, there's like this abstraction of like timing and so on. For like students before before 15 or 16. Future is what? Future is like Christmas or like holiday time. But then asking them to be like, oh, what do they look like in 10 years? That's very hard. That's why it's also a hard difficulty.
Considering that the generation that we are supposed to teach are the Z generation of kids who do not respond to the teaching methods that we are used to, like we have been taught all the time. They don't respond to that. They don't do as much outside as we have done.
Yeah.
So that's, like my colleague here said, that the industry, technology, advancement, ultimately, yes, smart people think new technology, and the technology is making our youngsters stupid. Because they are just doing that.
They're very good at that.
That's what it is, and it's very scary. So.
Yeah, that's another aspect. But I think that's what we're going to discuss hopefully tomorrow. But I think climate change is also like a huge opportunity to shuffle back the cards and to be in that innovative pedagogy where outdoor education or like science-based education, and we're going to do that very quickly soon with like very simple material, is one of the very key aspects that, I mean, we can do a lot of stuff with our hands. We can, like do drawings, and we do drawings, and we can do a lot of like little experiments just to look at very complex physics phenomenon. But we can gather that in very small apparatus, and we don't need technology to teach efficiently something that science has been, knowing for years and years and years with no technology that we have now. Can you just quickly go on your one?
So we're kind of
kind of wanted to put everything here that we know. So it's basically about excess consumption, so that we have too many people that have too many factories to make too many presents for everybody. That is going to burn out all the carbon that we have below. So the photosynthesis and burning is out of balance. It makes the Earth grow warmer and warmer. It makes our icebergs melt away, and all the bad things in our water and everything is kind of happening if we're not going to limit our consumption. That's basically what we have here. So there's
no more
some
gifts.
dead peas and
Oh, no.
dead apples and yeah.
That's sad. Great, and you put some arrows to represent...
to present heating waves. So the light from the sun and the heat from there, and also more from up the ground.
And it's interesting you're putting like dot lines for the atmosphere up there.
Yes.
Yeah,
It's kind of here.
Yeah, so it's kind of here, and it's very good because it's not like a line, right? There is no like clear separation. That's something that is very important, hard to
and also,
get, you know.
It's not only the fuels that come from the earth, but also some other minerals and metals and so on that are to put all the things together.
Yeah. Cool, great. All right, it's already noon, and what I propose to you now is to start to work on an experiment, and then we can make it like live. I don't know what.
We will have a lunch break at 1 p.m.
Okay. Yeah.
But we have an hour.
Yeah. So now, okay, let's do it. So we talked a lot about like all of that. You can gather just the drawings. And now what I want you to think about is how can we make a very simple experiment to represent the greenhouse effect that you can all draw there. What would we need to test? So let's do what we call an analogy, right? What would you like to use to represent the greenhouse effect?
What would we like to use?
What, if we study greenhouse effect, what do we study? Yes, the gases, but what the consequences do we want to study?
The climate effect.
Sorry?
The climate effect.
Yes, the climate effect. But then if we reduce it to the core of it, the physics of the greenhouse effect, what is the outcome? Climate is more like the general aspect. What's behind climate, by the way? What do we put? What's the definition of climate?
Weather in the long term?
Yes, weather in the long term. Weather in, say, 10 years or like 5 years long time. Also weather in the large space. Okay, what's behind weather? What component?
Sun and the clouds.
Yes.
Winds and waves.
But in the when we look at the weather forecast, what indicators, what data are we actually talking about?
Temperatures.
Temperatures. Yes. What else?
Wind speed.
Yes.
Rainfall.
Rainfall. So. And humidity. That's basically the main one. And that's basically what's behind climate. And when we talk about climate change, we talk mainly about temperature, right? So, if we want to do a simple analogy to represent climate change through the greenhouse effect, what are we looking at?
Some heating source.
Yes, we need a heating source. Heating source is an analogy of what?
The sun.
Yes. What does the sun has as an element? You were talking about heat, and if we want to make it very, like the sun, if we take a microwave, for instance, microwave does heat stuff, right? When we put like soup in the microwave, push the button on, and then heat the soup. The soup is hotter. Does it act like a sun?
No.
Not really.
Not why?
Because the microwave basically rubs the molecules together, that generates heat, but the
Yes.
sun doesn't do that.
Yes. But the sun, what does the sun have in difference with the... Or let's take a heater. If we call in the winter, we put the heater on. Does the heater is similar to the sun? Can we use a heater in our experiment?
No,
Why?
because it has the long wave,
Mm-hmm.
but the sun has the short wave.
Yes. And in other terms, the sun has heat, but also
Has light.
yes. And we're going to see the long and the short waves later, but basically we need a heat source that is close to the sun if we want to have a good analogy. So why not using a lamp? Okay. So that's the first aspect of the analogy. For the sun, we're going to use a lamp. If we go back to there, so which component, which data do you want to collect? If we talk about climate change, the main aspect we saw in the video is what?
Temperature.
Yes, so we're going to look at temperature. To look at the temperature, what do we use?
Thermometer.
Yes, so we're going to use a thermometer. Okay. Okay, now what do we need? We've got a sun. We've got ways to look at the temperature.
Different surface.
The surface, for what surface?
Water, land.
Water, land. So the general, I'm going to draw very quickly. The general aspect of what we were talking about, which is this effect of, okay, what we're looking at is more this aspect, right? So that's the greenhouse effect. We were looking at that today. So we've got the sun, so that's the lamp. That's the surface. Here, do we care if it's water or land? We want to go to like the simple way. Not really, right? So surface. Which surface do you want to use? Yeah, table is good. Let's do that on the table. Okay. Then what?
We need some kind of coverage.
Yes, what is the coverage doing in my drawing? What the coverage is representing in the analogy? Yes. Okay. Which properties of the cover do we need? Can we put
Glass maybe?
We need reflectance and absorbance of the heat or
yes?
of the light.
So
Radiation.
for the cover, you mean?
Yes.
So if we do, yes?
I mean, basically, it's. I mean, if you're talking about the oceans, then the oceans are darker. It absorbs more of the heat.
Mhm.
If you put basically a white or a reflective piece of covering, it reflects the heat away. Basically.
Yes. So you're talking about the surface,
Yeah.
type of surface.
Yeah.
Yeah. we can have that experiment, but that's an add-on. That's a different type of experiment. We may not have time to do it, but basically you can draw here. That's a black surface, that's a white one.
Yeah.
What are your expectations?
The black one should heat up more than the white one, essentially.
How would you get the data from?
I don't know. We could use a thermometer, maybe, on the black one and the white one. Basically, there's a temperature difference on there.
Yes? But that's not the greenhouse effect. That's more what we were talking before. We can do that maybe tomorrow, but that's the albedo. I'm very messy, I'm sorry. So that's albedo. Let's concentrate on here. So what type of cover do you think?
Something that's semi see-through.
Yeah?
Semi-see-through.
Semi-see-through. That's why it's quite hard, because we can choose anything that is see-through. So basically, the atmosphere is see-through, so it's like it's transparent. But it also has a component of keeping the heat, right?
We need to build a greenhouse, essentially.
Yeah.
We need some kind of like plastic or something that can let through heat as well, and some fabric.
So if we take a greenhouse, which are the materials that are used mainly for greenhouses? Plastic nowadays, and glass. And plastic or glass. What do we have here around me? Yes. I suggest we use glass, because the majority of the greenhouse are like built in glass. The ones that are in plastic have special plastic. If we use a plastic cup, that won't be, and there are like some specificities in terms of the thickness and all of that. But the glass should work. Okay. Now, how this experiment should look like, if you got time. Yeah, we have time to do it. Yeah. Can someone come and draw the protocol with my help, or with all of your help? I got 4 pens. The different, like the protocol we will use. You've got it or not? Oh, let's do that. Before we start doing the experiment, can you all just draw on one of the papers here your idea of the protocol?
Like the steps.
Yeah, or just like the design. Yeah, the experimental design. And also the steps and the timing and so on. Before starting to do it, before lighting your lamp on, I ask you to just do the drawings. And that's a step that is very important, and I think that's my mistake. We should have like done it later, and I forgot. Because it's important for the students to reflect before starting the experiment on how they're going to do it, what is the expected results. Sorry. So I'm asking you to do that step now. Before looking at the material, it's just more like draw stuff. If you do that, then what happens? What do I want to see? And to help you out, if we do an analogy, what do we have to be careful about? Because here we've got all of the material, right? We've got the atmosphere, we've got the sun, we've got a thermometer to look at it. Yes. Yes. Yeah, careful not to burn up. Careful not to break the glass. Careful, yes. But also, if you do an analogy, then you want to show results, right? You want to show the results in itself, or how can you conclude that your analogy is working?
Do a separate test to control.
Yes, you need a control. Okay? What's your control? What would be your control? Why do you need a control?
Control should be in neutral conditions, basically, and not in the glass.
Yes, exactly. So the control would be what's happening if the Earth doesn't have any atmosphere, right? We can't do that. We can't remove the atmosphere like that. But what we can do in our analogy is to have planet Earth with an atmosphere, so surface table with glass, and a planet Earth without atmosphere. And then we can say, okay, initial temperature was the same when you started the experiment in both of the planets, both of the table. Now, after 5, 10, 15 minutes, there is difference or there is no difference. And then we can conclude, okay, the glass is acting and blah, blah, blah. Okay? And the food source, like the food source. The sun is the same, so we're going to use the lamp, the same lamp for both experiments. Okay? So I'll let you draw very quickly, and then you can start the experiment. And think as well as a protocol of, like, you know, getting the data, collecting the data. I suggest it could be fast. In 20 minutes, you're going to have the results, I think. So, or even 15. So you can draw the table, you know, like collecting data every 2 minutes. You can do 15. Okay, let's do like every 3 minutes, that will be quicker, up to 15 minutes, okay? And then we need 2 thingies, right? Maybe it's not the best setup. Not the best, it's not the best at all. Yeah, I should have done it like the other way around. Yeah. So that'll be here. So like group 1. Very, very good. Using the and so not before and after, but with atmosphere and without atmosphere. Okay, yes, better. And yeah, plasticine, you found a little bit of plasticine, is to seal the glass.
We did 2 parts. One is the without greenhouse, and one is the with the greenhouse.
Oh, and you want to get the temperature before and after of that one?
Essentially, yes. How much it changes, basically, because the lamp is turning on that one as well. So how much it's changing?
Yeah, that's very clever. I'm worried. I'm worried that if you do that every time you manipulate it, you get every minute affect the temperature. Also, no, what I'm more worried is like this type of thermometer won't get you the real temperature. You know what I mean? Well, that's a very interesting setup. You know, it's like they're not accurate enough. It's not like that you put in your bottle. The temperature from the ground, and therefore we need more. You got any more information? That's why you're going that direction. What if you got 2 thermometers? What would you like to do? I'm gonna find another one for you. Do you? How many thermometers do you? Yeah, but it's to have the control and the if not, we can make 2. So we got 2. Yeah, but then so this is perfect. And one here, and then we got only one.
I think we have more.
Okay, perfect. Yeah, well, you can do that, but then the idea is to try to reduce as much as variation as you can since control and the test group. So the best idea is to set the same numbers. And try to have the at the same distance as possible. Then you see reduce the variations. Yeah, I think that the animal so now you got 2 thermometers, right? What would be the best way to get temperature? Oh yeah, I see what you mean. Well, by surface, I meant not the actual table, it's more like the hair on top of the table. So if you put that here, then you'll have the temperature around in the air. It's like air temperature is more than the temperature of the table. Because you open the glass, that's what you mean. But then that's why you use the plasticine, the blue tap here, to seal. To do that, and then put some blue in the mouth. Okay.
Now we get it.
Yeah, no,
okay. Okay,
oh, I'm going to do another table. Well, here, you got space, right?
Kas see katsuvad päev kiiresti see
works like that. Yeah, but I want the
silmaga
yeah, good idea.
teemegi nii. Ma teen siit maksumuse, pärast saab selle väljapool kinni. Ja ma ei taha, pane ümber.
That's why we do like it's also like an interesting example of okay, well let's do that. Then maybe if you got time, can we do the experiment by shuffling them? But that's also interesting because like usually this is very simple experiment, but sometimes it doesn't work. Why it's working, what's in the protocol, changes on from that experiment of what science. Different advantages, experiments to make it work or not and to succeed. But those points, these experiments show more what we call companion effects rather than greenhouse effect. And actually it's a very simple way to show this in an analogy that is very far away from the reality. So that's why we're doing this as well. So I do that on purpose. Yes, it's far away from reality. So, no, it's the main aspect that's far away from reality is that two aspects. Is that glass is like the one surface, and atmosphere is more. There's no like line between the atmosphere and the greenhouse gases are everywhere, not only at the surface. So that's the main aspect. And also the other aspect is that here the air is trapped in the glass, so because it's trapped there is no heating up. So therefore the heating up, the main aspect of the heating up, if there is a heating up, is more that the gas is heating up. Rather than transfer from like warmer gas, warmer atmosphere, air from outside and inside the glass. That's what we call confinement. Yes.
Inimene peab midagi tegema. Kas mõned tublisid ütleb ka mulle, et nüüd on nagu veebis nagu šokeeriv.
that much difference. Is it different or not? No. Staying a bit. Maybe we have to go more than 15 minutes, maybe 20 minutes. I can add one more here.
Siin on fondid siin alla ja siis sa näed kogu aeg, kus tõused. Sa kasutad muidugi. Siin on, ma arvan, et see jutt või siis üks variant oleks ka see, näiteks kui ma olen arvutöötaja, üks variant oleks see, teha need 2 pool tundi või tundi aega ja siis anda meile nagu infot otsida ise, miks nagu ei, tegelikult läheb. Ei. Mina olen ametlik. Mina olen selle, et ma teen sõnadel ümber liikudes. Ma saan vaadata. No siis tuleb see läbi rääkida. Maastaabuses proovisin neil lihtsalt see arvuti uurimist internetist otsimisest juurde, nagu et saaks sellest infostust aru, mis on tähtsad asjad. 10 minutit on tõusnud. Minutiga on tõusnud praegu järgmise 5 minutiga see on Siin ei tea, mis täpselt.
We can stop at 18 minutes. I don't know how you're going up to 2 hours later. I mean, once we have like reached 18 minutes or even less for some groups, we can and you can stop my table is very ugly. Sorry. But here we can collect the data temperature for glass, so with atmosphere, and here with no glass. And I put group 1, 2, 3, 4. So there can be 1, 2, 3, 4. Oh, that's funny group. Okay. And then the fifth group will be, oh my god. Here. No. Here, okay? Group 4 and 5 will share the same box. I hope it's fine with you. Climate change education is all about cooperation, so here we are. I'm forcing cooperation between two groups. Okay, who's group 1? Here.
Yes.
Okay. Group 2, group 3, group 4, group 5. Okay. Should I write? All right. Okay. Which color?
Doesn't matter.
Doesn't matter. Okay. I'll go for black. No. Blue. Okay. Glass, 0 minutes. 25.
Oh, glass. Oh yeah, they won't be 25, this will start.
Okay, 3 minutes.
We've got 28 and 28.
6.
29 and 28. Then we've got 29.5 and 28. Then we have 30 and 28.2. And we have 30.1 and 28.2. And then we have the same results.
Okay. Group 2.
First one is 23.5.
Yes.
And then it's the first one is 25.
Sorry.
This is the first.
So that's atmosphere.
Yeah, we don't have the controls on.
Oh yeah. Sorry. Okay.
So here it's 25 and 23.5.
Okay.
6 is 26.5. And 27. And then it's 28. And 28. And the same. It's stopped, so it's 28. Yeah.
Easy. Okay. 3, 24, 24. All right, thank you. Okay. One of the groups. Okay. Estonian. Yeah. Okay. Yeah. Okay. That'll do. Perfect. Oh, no. Oh, I mixed it up, sorry. Oh, no, that's good.
If you cover it up, it makes a noise.
You cover with what?
No, don't move it. Okay. Oh, okay. Okay, then it's something else. I think.
A sensory alarm, yeah?
Maybe. I don't know.
Any other suggestions? Is it alive? No. Is it electric? Yes, okay. What else? It's white. It's beeping sometimes. When does it beep? Uh-huh. Yeah, you moved it. But if you don't move it, it's good. Okay. Okay, you make a sound. Make a sound when? Light? How can we test if it's light sensor? It's dark or it doesn't. Okay. So we've got different aspects to test. How would you differentiate if it's light, movement, heat? You can use anything you want, but you can't move the thingy. The electric device. So for now we know that it's maybe just a hand sensor.
If I blow here,
Yeah, right? So you blow.
it's not air.
It's not hair. It's not air.
Air, yeah.
Yeah. With your hair. It's not hair either. But hand.
It didn't react to the hair. It doesn't react to the movement. Yes.
Uh-huh.
It's warm.
Yeah, right. We need some heat. How can we actually prove that it's not movement, but it's heat?
You can try the paper.
Yes? Okay. Let's try the paper. So the paper is what? It's cold? Is it cold? Regular, yeah. It's ambient temperature. Okay? It's maybe hotter than the ambient air here. That's my hand. Okay. Oh.
Shouldn't do that, should it?
No, because this one's like colder. That's my background, right? Okay, let's do that. Let's put that. Okay. That'll be the new background is white. Okay. Very good, Matt. Okay, so that's the new background. Okay, so paper which is the same temperature as this paper is not beeping. So we proved that it's definitely heat rather than movement. Another way to prove it maybe, set it on fire. Is it hot hands? Is it because your hands are hot? Is it only like, you know, look like a differentiating or beeping when it's like hotter?
Change of the temperature that's inside that.
Yeah, but in what sense? We tested only like hotter, like warmer. My hand is warmer than the background, so it's beeping. How can we test something more widely? Yeah, colder. Yes? Okay, so that's a glass with no water in it. So the glass has room temperature. What if we put some cold water in it? It's cold. No, it's a thick glass.
Yes, we know.
Yeah, it's very thick glass. It does beep. Okay, and now we've got also the opportunity to do the same with warm water. If there is some hot water there, then do the same. Right. Yeah, but if you do that, then why would you differentiate? What would you say? Well, like a student can say, okay, it's beeping when there is a glass with little dots with color in it. It's not beeping when it's like a transparent glass. So you would need a transparent glass with hot water and one with warm water. And that's the thing that is good with warm water. If there is some hot water there.
Siis on tähtedega kas, siis oleks vaja tähtedega kas ja kümme, tähtedega kas.
I thought they were. That's okay. No, it's fine. If we would have hot water, we would have like, you know, 3 different types of glasses. One with normal temperature water, one with hot water, one with cold water. And then you've got the complete demonstration that it's beeping only when the water is either higher or lower than the ambient air. So basically what's happening, this is a detector of heat difference between the background and any object that moves in. Okay? Any object that moves in with a different temperature. Okay, so why am I showing you that? Let's make more of this experiment. I do have your screens here with different properties. One is quite interesting actually. Let me just something to read. Okay. This is a screen cardboard, right? Can we see through? Can you see my face? No. Put it here, doesn't beep because like temperature. And now I need another hand, or like any hand, to see if it's detecting or not.
Where?
If you pass it through here, yeah. Does it beep? No. So this can detect the heat, but this little one blocks the heat, right? So this is opaque, or it doesn't. We can't see through it. so the light doesn't go through, and the heat neither doesn't go through. Okay? How about we try with glass? Can we see through? Yes, it's transparent to visible light. How about, what do you think would be the behavior of the glass with the heat? What do you expect? Let's see. Wow.
Am I dead?
I think you're dead. But the only explanation. You're not hot enough. Okay, another hot hand. Okay. This hot hand was beeping before. Your one wasn't beeping, so yeah, that's okay. So it's not beeping now. Yeah. Weird. No, look. Still not. Okay, I'll remove the glass. Put your hand now. See? So the glass is transparent to normal visual radiation, visual light, but it blocks heat. It does block the transportation of heat through radiation. Interesting, isn't it? How about plastic? Can you see me? Mm-hmm. You can see me too. Good. Give me the hand. No, 2 hands. No, it's more by moving in now. Yeah. Passing it. Pass it. Yeah. It's not doing anything. So that's also is transparent to
Just visible light.
visible light, but also to heat. This one is a bit thinner plastic. Let's try again. I can do it if you. So see, that's why I didn't want to use plastic glasses, because you've got 2 different types of plastic. This one is not, very, very thicker, but still, this one has the property to block the heat, but this one doesn't have the property to block the heat. Now, an extra one. This is garbage bag. Very trendy. Can you see me through?
Yes.
No. My face, I mean. How about we put a hand quickly. Oh, maybe this one's not working. Well, it's good. Doesn't detect the heat either. It does. Well, maybe because there are like 2 levels here, but anyways, that plastic garbage bag is the type of plastic that is opaque to visible light. It doesn't go through, but it's transparent, or just let the heat going through. Okay? So basically, we were exploring the material of a greenhouse, for instance, and that's why we were thinking before, greenhouses are usually in glass or in plastic, thick plastic preferably, and that's because they can go through the heat can pass through it. Sorry, the heat cannot pass through it, I've got it. But can pass through the other materials. And so that's the little experiment I just showed you. And the idea is to explore here if it beeps or not, depending on different type of little screens. And if we note here, it would be doesn't beep with wooden, doesn't beep with transparent sheet, but then it beeps. No, sorry. yeah, transparent sheet, paper sheet, it won't beep, but it beep with garbage bag. So basically what's interesting here is that the glass or the transparent plastic, they have two properties that are very similar to the greenhouse gases. They can go, I mean, they can let any long waves coming through them. They can let pass the light from the sun with the energy that is conveyed by the light from the sun and the heat that is conveyed by the light from the sun, but it's blocking everything that is coming in other type of long waves that are the invisible light or the infrared lights. Okay? Basically, what we see, what we call visible light, has this range of like from ultraviolet that we can't see, but the bees can see them, that's a little trick, till the infrared, and the infrared we can't see it. But the infrared has the property to bring heat from one source of heat to another. It also has the property of being the transportation of heat of anything that is cooling down. So the table is radiating because it's heated up by the atmosphere, it's heated up by the sun, anything. I'm radiating also infrared. And so if you use an infrared detector, I don't have any pictures here, but if you use like you know, you've got cameras, infrared cameras. If you use an infrared camera, you can see people like radiating, right? Because we are like warm blood animals. So we produce heat, but we're not like, you know, we don't glow in the dark. We're not sun. That's because we're producing heat, but not as much heat as the sun is producing. So basically there is a degree of temperature when the invisible light becomes visible light, okay? So it's around like 700 degrees. So the Earth is invisible because it doesn't produce as much of energy as 700 degrees. Actually, it doesn't produce like temperature. There is some remnant temperature from the Earth formation after the Big Bang and so on. There is still some like temperature going out, with very, very minimal temperature, because the Earth's cooling down was very early on in the history of Earth. But the majority of the heat that is going out from Earth that we can't see, because it's conveyed by infrared radiation, because again, the temperature of the Earth is less than 700 degrees. All of this energy is actually the re-emission of the heat from the sun, okay? And that's what is trapped in the atmosphere. But then you've got different type of energy sources that are more than 700 degrees, and therefore we can see them. You can see the sun, obviously, because it's like more than 100 degrees. You can see that type of lamp. We can see the lamp that you put on. You can also see lava, but lava is at the limit of the temperature, like visible temperature. And that's why also it's like pretty close to bluish, like you've got all the ranges of the color, and it's not like a very bright yellow color because it's closer to the end of the visible light and the infrared light. So all of these sources, they do convey as well a bit of infrared, but the majority of the heat is conveyed by like all of the other waves. I don't have the graph here, but if you're interested, I lost it. Uh-oh. Let's see. Here we are. Yeah, so it's a bit more technical. It's like physics, really. But the thing is, you see here, that's the temperature in Kelvin of a source of temperature. And if it doesn't reach that spectrum, then it stays in invisible infrared light. And the sun is around there. So the sun has majority of visible and ultraviolet and a bit of infrared as well. But then all of this heat is going through the atmosphere. There is no issue at all. But then everything that goes in infrared is trapped by the greenhouse effect in the atmosphere. Okay? So that's the part that is a bit tricky, is that we've got two types of light, or like radiations, one that are visible, and those ones can go through the atmosphere, reach the Earth, then it goes into the Earth entirely, that just gather the energy and then bring back the energy back to the atmosphere, because it's cooling down, okay? And then once this energy is going outside the surface, when it's like, you know, going out in the air through infrared radiation that we can not see, but we can hear from here, part of this infrared is trapped by CO2, methane, water vapor, or nitrogen, and it's the same process, like getting all the energy, and why the molecules are exciting. Part of the energy goes up in the space, and part goes down. And that's why sometimes you've got schematic representation of bouncing back and forth, because basically it's hard to represent. It's very hard to represent the greenhouse effect. Basically, all of these little molecules in the atmosphere are gathering energy and bringing back down, but then it's maybe trapped by another molecule, so it's always bouncing. And a good analogy for me is like it stays, like part of the heat in form of infrared will stay in the atmosphere longer than if there were like no greenhouse gases. Okay? All right, so what I propose now is that we go outside and we explore that concept a bit more. Because what we see now is that we've got a good analogy of a greenhouse, but does it actually represent the atmosphere? A glass or a greenhouse has limits, right? It has just a barrier, a frontier between outside and inside. But is it the same for the atmosphere? Do we have like a glass layer on top of the... I don't think so. Otherwise, for like, you know, Elon Musk to bring all of his bloody satellite, it would be hard. No, there is no glass layer. The atmosphere is like, you know, a mass of different gases, and the concentration of gases is reducing by and by when it goes out from the planet because of the attraction of the Earth, right? So at the end, it's more like there is less and less and less and less gases. So there is no layer. So that's where, as well, the analogy is wrong. Because in that sense, an analogy would be, here would be like a very, very thick glass, and then less and less and less and less thick, and no glass at all. And we can't have that, right? So that's why we need like maybe another analogy. Just quickly, we mentioned them, and we're going to go back to them, but that's the major, the only greenhouse gases that are present in the atmosphere of our planet. Other planets may have some other ones, but our planet has those ones that react, as we were mentioning. They react like the glass. They are transparent to visible light, but they gather and emit all of the infrared radiation they can find in the atmosphere. So carbon dioxide, methane, nitrous acid, and F gases, they are all increased by human activities, and water vapor is not increased by human activities, but like as a byproduct of climate change, there is more and more water vapor in the atmosphere. And they do react like the glass, but in different ways. A bit like, you know, thinner plastic or like thicker plastic. Let's say those ones, the fluorinated gases, are very, very, very thick glass. They trap very, very intensely the heat by gathering that infrared radiation and doesn't let it go, so it just stays more. But hopefully there is only few percentage of those ones in the atmosphere. Those ones are, I think, are more like used in fridges or like in technical area or like very specific industries. Then you've got nitrous oxide, which is less present as well, but has like a higher power. We call it like the global warming potential. So basically, it's like how much more potential of warmth can it have compared to carbon. Carbon dioxide is 1, and then you've got like 1 more.
And it's like a combination of like how long does it stay in the atmosphere and how strong this component of like trapping heat is for these different gases. And nitrous oxide, you know where we can find it? So it's mainly in agriculture. They are like a byproduct as well of fertilizers, that we put in the land. They are also a byproduct of some like chemistry industry, but it's mainly fertilizers. Methane, we talked about it when we talked about cows, burping, rice paddy as well, when you produce rice, but it's less strong. And then a lot of like pounds and humid areas, and permafrost is like releasing as well a lot of methane. And food waste, food waste a lot. And carbon dioxide, that's the most famous one. And we all know that it's coming from the combustion, mainly from the combustion of the fossil energy. All right, so it looks a bit like that, right? If we, for representing it, and I think for me it's not the best way, it could have been more of a gradient of blue, and then it's like fading away towards black. Because I don't like the line here. I think you got me now. But anyways, one representation would be like the heat is coming from the Earth, tries to escape, but then you've got greenhouse gases that just catch the heat and bring the heat back home. What if we were all heat and greenhouse gases? And what if we all go outside now? Yeah. Let's go? Okay, I need 3 teams, but let's go outside and find a nice spot. Yeah, we did that with that thing, I don't know why, I think it's more the communication team that, so it was good because we've got our name in the thingy. But you can do that with normal clothing and just separate the class with okay, you've got colorful, or even with some stuff. But yeah, I found it's quite interesting game. We adapted it. It was developed first by a team in Ireland, I think. It works since quite a long time on climate change and sustainable development education. And we adapted a bit to fit that analogy. All right, so do you think you would do the same drawings as this morning after we did the 3 types of experiments? Also because it's always not very clear, and we're always tempted to work directly on the consequences and on the impact of humans on the greenhouse effect. But to me, climate change education needs also to have this first step of understanding the science behind it without talking much about the human activities. I think it's a very important step because it goes into the curiosity of the students, it goes into the science labs and how do we build science, and we evacuate first, and we don't talk first about all of the human activities, the burping of the cows and all of that, because we've got time to talk about it later. And also because without understanding the process, or without having this a clear idea of how it works, then everything we say after that won't be as strong and won't be assimilated as good. So I think it's very good to step a bit back from all the media, all those kind of urgency of human causing climate change and so on, and having this space of exploring the physics behind it, exploring all of the different elements we can have. We can add to that other experiments. We won't have time to do them today, or it's not necessarily on that topic per se, but we can talk about the albedo. We're talking about this morning about it. It's a very simple experiment, same thing. We use different colors, black and white, with a thermometer behind it. And in that way, we can explore different aspects of the climate system with the students without going first into what human activities are causing and so on. So how about someone do another drawing of the greenhouse effect after we saw everything we saw? Would anyone be nice to do it? There's some colors here, pen, can be very simple. Can be like a pair of people, like 4 or 5 people. Ah, good. Just do it like step by step and explain what you do, and then we can comment on it, right? So what would you represent first? What do we need? What is it? Okay. What do we have to be round? Yeah, we've got more paper, so you can do one first and then we go. But why do it have to be round?
Because that's the shape of the planet.
The shape of the planet, yes. But then the greenhouse effect as a physics phenomenon. So they have to be on a round planet. So maybe if it's simpler for the arrows, for everything you want to represent, you don't have to have it round. That's also something we need to practice with the students, is that an analogy is not a representation of the reality. And a schematic representation of a physical phenomenon is not necessarily needing, to be accurate. That's better. Okay. So, what do we have here?
That's Suur Munamaa. It's the biggest mountain on Estonia.
Okay.
Yes.
I like it.
Yes.
It's green, it's beautiful. Then on top of it, what do we have?
It's the air fading into the space.
And then we've got a visitor from another country.
George.
Okay, on top of that, what do we have there, further away from George?
Sun.
Yeah, sun.
Sun very yellow.
Yeah. Again, it's all conventions. A schematic representation doesn't have to have the same colors. Why not having, if you don't have, yellow? Okay? George from the sun. Okay, so now something we didn't really explore is what's happening before all the game we did. What's going on from the sun?
Heat's coming.
Yeah, heat is coming. The heat is coming with the visible light.
Yeah.
Okay, so we can draw like a big, what's that? Is it good?
It's visible light.
Yeah, we can see the light, perfect. But then you can draw an array, a yellow array, but a thick one.
Yeah. Visible light.
Yeah.
Yeah.
Yeah, you can go on top of it, no worries.
Yeah, so it's almost through right between the eyes.
Yeah, and then part of it, if you got like a little, go for it. Go until the earth and make it like quite thick.
Yeah.
And like yeah, perfect. Yeah, right. Okay, perfect. So what's happening with this light? That's good. The visible light. What did we say about the albedo effect, for instance? So part of the light directly bounced back to the space. It bounced in 2 different ways. May I?
Yeah.
So say here, we've got just a little cloud. Okay? So if you got a little cloud, what's happening is that part of the light just goes directly here, okay? So we reduce a bit of this thick layer by having a bit that just disappears back to space. Okay? And that's also this reverberation that makes the clouds so yellow, so white and so bright when we see them from space. I don't know if you've been to space. No? Okay. Me neither. And I don't wish to go to space, it's polluting. Then, on the surface of the planet, we've got also a second arrow of ray emission, no, sorry, bouncing. So it's not ray emission, but it's just reverberation. And that's why we can see Earth from the sky. I mean, that's what they say. Okay, so now we've got this amount of energy. What happened to that? What happened to that energy here? Yeah, it goes inside the ground, and after that?
Energy comes back from the ground.
Yes, in what form?
Power.
Yes, and what else? Heat. Heat. Okay, how about we use red? Because we can't see infrared, so we can try to see red instead. And that you can do like waves, more of the wave stuff. It doesn't have to come from the point, it can, yeah, very good. Exactly. Okay, perfect. What's happening to those waves? What do they
Trying to
mean?
get back to George.
Some of them can go back to George. Remember, there are like 5 of you guys who escaped. So 5 of you arrived to George. And then what happened to the 5 other ones?
They got trapped in here and got pushed back into the land.
Yep, so you can draw just little molecules. And those molecules actually, yep, the CO2, if you want to do it like nicely, it's 2, oxygen, 1, yeah, like that. And methane is 4. Okay, so they trap, and then a good way to represent it, they trap and then that bounce back here, but part of it just goes up. So you see that some of it just goes out, but the majority will stay here. Okay? And that is the case since there is still some greenhouse gases here. If by any chance that will not happen, and there is no way it will happen, it's not good if it happens. If by any chance we remove all of the greenhouse gases from the atmosphere, then all of them will escape, and the Earth will have just, the heat won't be there anymore. So a planet without an atmosphere, a planet with an atmosphere with only gases that are not greenhouse gases will be something like minus 19 degrees, which I never really encountered in France, but you might see that in Estonia sometimes. Yes, but not for long, thanks to climate change. So basically, if we remove all of those ones, and we have like a hypothetical atmosphere without any of those greenhouse gases, land, all of the Earth will look like Estonia in the midst of winter, which is good. We have sauna, ski. Actually, it's not that true, because the atmosphere also has a role of regulation between night and day. So it's more like it would be minus 40 or plus degrees during the night and plus 40 or more during the day. But then you've got an average of minus 18 degrees, which is not a temperature ideal for evolution of life on the planet. we would have only what, tardigrades maybe, or all of those very extreme badass.
What would be done in the case of like springs and summers in places like this?
Yeah.
So it wouldn't be natural, it would be produced in a building.
Yes.
Where if you want to experience spring,
You go to
Antarctica, there's a big massive greenhouse where it's heated with electricity or whatever.
Yeah.
It's like also it's
Impossible.
no, it's possible, but it's like it's fake.
Ah, it's artificial.
Artificial, yes,
But yeah, but then it wouldn't be possible because humans wouldn't be living there, so we wouldn't be able to do that. But there are some planets on space that are experiencing that type of magnitudes between. Venus, for instance, has a huge variation between night and day. Sorry, because one of the reasons is because they don't have the same composition in the atmosphere. Okay, so you see the representation here is a bit different than the one we did, and still, for me, it's not the best one. But what is good, at least, is that the infrared radiation doesn't come from the same point here, and you've got the bouncing here, which for me is not necessarily at the surface. What is good, nevertheless, is that we've got a fading phase here, so it's not a line. Okay, so what's happening with all of our friends, the blue team and the black team, or the blue team first, only the blue team is out here. You've got part of this infrared that actually never arrives in space, but just goes back to the surface. And basically, in our game, what we did is like you go back to the planet and then come back. But what's happening physically on the planet is actually that infrared conveys heat. But the same process as what's happening here. It goes on the surface and just heats up, and then the surface Earth absorbs the energy from here and re-emits it. So we've got a bouncing. It's more of a bouncing, but it's not like, you know, in a mirror. It's not the same as here. It's more like you take and you give back. You take and you give back. Okay? So that's hard to represent on a schematic phase. But by doing it in the game, you can feel that, you know, process. And also, like, it's very hard because I do that, like, you know, step by step. But it's just happening in 1 millisecond, it's like all happening at the same time. That's also like a difficulty to represent it. Okay. So it's warming, and then an analogy would be to have a little cute dog covered by a plaid like you have here. It's actually a very good analogy for the greenhouse effect, because all of these greenhouse gases are acting like a blanket. Particularly when you're cold, I mean, you're a source of heat, as we all know it, because we're warm blood. So if you put a blanket on you, the blanket doesn't produce heat, right? So the heat that is, association of heat, is that your infrared that are escaping from your body are blocked by the blanket, and then just stay there, and the hair between you and the blanket is warmer, so you'll feel warmer. Okay? So that's the same process. Except that from the planet doesn't have any blood. It's not a warm blood planet. So it doesn't produce heat per se, but the heat is coming from the sun. So the blanket doesn't go well with the planet, because the sun doesn't reach the body of the little dog unless you would have like a transparent blanket made of glass. That doesn't exist. So you see, there is some variation, but all of that means that we've got different analogies that always work, but at some point it doesn't work. There's always something that we can't, so that's frustrating. So a schematic representation that would work a bit better, and we're still working on it, is that without greenhouse effect, there will be something like that. So you've got the energy, I've got my little pointer, what is it? Oh, it's there. Oh. Okay. here you see you've got this amount of energy coming in. Part of it just goes back, bouncing on the clouds, bouncing on the surface of the planet. Then you've got this part of it, this amount that goes in. And this same amount goes out. So if you do like if you put all of that together, that plus that, no sorry, that plus that equals this length. So you've got the same amount of energy coming out from the sun, reaching the planet, and the same amount of energy you find it in the space. Now with the greenhouse effect, you've got the same thing here, but here you've got this like thick arrow at first, and then everything's happening here in the lower atmosphere, because all of the heat coming out in infrared shape goes here, gets reach out a CO2 or something, parts come back, parts come up, and then just stay there. It's more like they stay a bit longer and longer and longer, and that's heat up the atmosphere. But then if you look at it from space, from elements, whatever satellite, you would have the same amount of energy. So it's more of a retention of energy here that ends up with an increase of temperature. And that's why I said to you, if by any chance you remove all of the greenhouse gases here, we will have this thicker line just going down, and we won't have any retention of energy anymore here, and they'll be like that. Is that a bit clearer? Are you alright? Okay, so that's a long day to just talk about the very unique phenomenon, and I think for me, we need that basis, and not that full day and so on, then to talk with cows, and so on. Okay, we just did the common of the drawing. So now what's happening with here? Oh no, what I can do before, I can go through so it's not included in the presentation because we developed it like very recently, but we developed a small multimedia animation, which I don't know where it is. I bring it. Okay, here we are. Okay, so it's in French, sorry, I'm going to put that in Estonian. Oh no, in English, don't have it in Estonian yet. Okay, so that's a little multimedia animation just to show you, that we developed, just to try to show you as well the different processes that we explored today. With the animation we explore the role of greenhouse effect, how it works, and the impact of human activities on it. See, so we go on to with human activities. But first of all, what would the Earth be without greenhouse gases? So same, radiation coming from the sun. Second step, crossing the Earth's atmosphere, part of the radiation is reflected back to space, another part is transmitted towards the surface of Earth. So we've got the first bouncing part. Ensuite, after that, arrival on the surface of the Earth, back of the radiation reflect back to the atmosphere, and finally the other part is absorbed by the Earth. Energy storage. The temperature of the Earth's surface increases because it receives energy from the sun. Okay? We've got two types of filters, which are the bouncing ones. And then finally we've got that amount of energy, the second arrow, right on Earth, and just increase the temperature of the surface of the Earth. In the ocean, it's less than in the continent, but still everywhere there is increase of temperature. Then, emission of infrared radiation. The surface then emits infrared radiation which carries heat to the atmosphere, cooling the Earth's surface. So it lasts in the space. So therefore, we've got a temperature of minus 18 degrees on average, because all the planet just doesn't keep the heat because there's no blanket. So it's just cold. Now we've got little molecules. We don't have George, we've got those little ones. What's happening then? same thing first, same thing, same thing, same thing. Then infrared, same thing. And then some gases in the atmosphere absorb some of the infrared radiation, preventing all the heat from this radiation from escaping into space. So here in the representation, it's just like one arrow, but in your mind you know that there is this like effect of absorbing, then we're emitting in both directions. But in average, we've got half of it, or here is a bit less. If all of the energy will be captured by all of the CO2 in the atmosphere, then you'll have half of it going back down to Earth. It's always the same. But because some of the heat is now trapped, and that's why at some point, even so we just put more and more CO2 in the atmosphere, they will reach a plateau. There will be one day, or hopefully not, but there will be one part of, even if we put more and more and more CO2, then they won't, you know, all the infrared will be trapped and goes down, so the increase of temperature will just be the same in plateau. But that won't be now, that will be a lot of time, if we stay the same as we are. So yeah, part of it just goes back, and then there is a new temperature, which is around 15 degrees. So that average temperature is the average before I mean, since even Middle Age, since the last glaciation, we are like around 15 degrees. But remember the graphs I showed you with CO2 and different temperature? They were like back in time, during like, you know, dinosaur times and Carboniferous time and Jurassic time. The temperature was warmer, around like 16 to 18 degrees. So they always like have those radiation that we saw. And they are due to like the combination of the sun and different orbital changes, so it's all natural. Okay, so the greenhouse effect refers to the fact that the Earth warms up due to some gases naturally present in the atmosphere. These gases absorb some of the heat from the infrared radiation emitted by the Earth. And without them, this heat would escape into space. So thanks to them, the average temperature of Earth's surface is about 15 degrees, and both are the greenhouse gases. So that's big. Well, thanks to the greenhouse gases, but also the presence of water on our planet, that we are evolved with different species, biodiversity, and human on top of it. So now what we wanted to show is all of this process of checking out which gases are actually causing the greenhouse effect. So it's just like a little representation of what's happening when you put infrared, so like a laser with infrared that we can't see, and then you excite some different gases in a little box here, and you check what's going on. It's a bit like when we put the glasses here, right? You check if we can have the infrared, or if you can feel the heat between the screen. And the screen here has CO2. So you see, you reduce the infrared. So part of the infrared radiation passes through, and part is absorbed by the gas. And they emit in all directions, so that's why it just stays there, because they all emit, re-emit, absorb, reabsorb, and re-emit. Okay? And then you got a little scientist here, and she's like writing down carbon dioxide. It's not the most powerful greenhouse gas, but it warms the planet because it is emitted in large quantities. So then you can go back to laboratory, and you can observe, for instance, methane, and then it's just the same thing I was showing to you. There is like a gradation of like if it's a strong or not strong greenhouse gas. And if we look at dioxygen, there is nothing at all. Absence of re-emission. So it's a bit like with the plastic bag. When you pass it, the infrared radiation goes through. Okay? And then you can have a look at planetary science, just to look at other type of atmosphere. So on Venus, it's stronger because you've got way more CO2 in the atmosphere of Venus, and the atmosphere is way bigger, and you see that the temperature in average is way stronger than on our planet. So we get lucky, in a sense, compared to Venusian people. And on Mars, that's the opposite. There is no or very, very little atmosphere. So the temperature is like minus 63 degrees, which is a bit more like Estonia in winter. So then what we were looking at was the Earth before the Industrial Revolution, and then you've got what's happening at the end of the century. If we do nothing, we've got an increase of temperature. Okay? So if we go back to presentation, just want to show you very quickly some graphs. But then the idea is just to discuss more what we saw today. I'm going to go through that very quickly. Another way, so now we saw that scientists at some point found out, by looking at different stuff, also looking onto it through this ice carotene, that there is a link between greenhouse gases and the increase of temperature. And then they did other experiments, and then they finally did some simulation to confirm that aspects and to confirm that human activities are causing the greenhouse effect, the current global warming. So that's through simulation. So basically, what's happening, we can simulate nowadays with a lot of like computer and coding and so on. We can simulate different planet Earth and through history, and we can simulate the atmospheric concentration, and therefore we can simulate the increase of temperature through different simulation. And they did this type of simulation where they have natural only, so solar and volcanic effects. So say they have 1,000 or like, even millions, or maybe just 1,000 of different simulations through different computers and so on, of a planet that at some point will have a huge volcanic, or because of the solar system, we'll have some variation. And that's why we've got those lines. So that's the average of the simulation, but then you've got the different simulation that goes into that. So the blue one is what's happening on the planet Earth, where human doesn't have the same activity as we have now. So there is no implication of excavating and burning fossil fuel, for instance. Then they did the same thing, but they added human activities on top of volcanic and solar radiation. And what they found is that we've got a line that just, is quite similar from the starting point of the century during the Industrial Revolution. And then at some point just drops, and then you've got the brown line just goes up and up and up into this anomaly in temperature, while the blue one just stays stable, almost around 0. So you see that natural variation should not affect, according to all those simulations, any changes of the current global warming. If you do simulation for like 1,000 years in the future, maybe at some point, with only natural and solar and volcanic, you will have like an increase or decrease that will correspond to a glaciation or interglaciatic era, which is caused by natural effects, okay, of the climate system. But then, if you go there, you see that there is this line that goes up, so there is a changes in the temperature globally. Then, in the black little line here, that's the observed observed temperature. So it's an average of all of the observation on the planet since that day thanks to different like measurable station, and we used to have like a lot of stations with thermometers, and now we do that with like a satellite and so on. And you see that that black line follows very, very closely the simulated human and natural line. That's a proof that green, like the global warming that we see now is due to human activities. So it's a combination of like observations from the ice caps, for instance, observation of temperature on the planet, and simulation that helps out scientists to clearly say what's happening on our planet with global warming. It's also on top of that what we saw in the animation, all of the laboratory investigation they did with the little gases. Okay? Okay, well, we can go on that path if you want, or we can change a bit. I don't know what you feel like. You're all quite tired, aren't you? We ran a lot. Just to briefly go into the deep and dark side of climate change, it's not only global warming, it's not only, and that's why we talk about climate change rather than like climate warming. It's like changes in the climate, in all of the components of the climate, and as we were discussing at first, climate components are the same as the weather component, and it's on the larger scale. So it's not only temperature, but it's also precipitation. And here you see a map of changes, the trend of changes of precipitation between 51 and 2020. Oh, 10, sorry. And you see that some areas are more and more arid, like Spain, south part of France, Sahara, like all of the desert part are like increasing in the area. And some other are more like wetter and wetter. So it's more like there is like an increase in the trends that is occurring on top of like all the extreme events of it. So here you see that there's a change in percentage of the population between those dates and nowadays. In the population that are experiencing desertification, drought, or the fact that there are like still wetland, and so there's like an opposite curve. So one is the number of people in percentage that experience more and more desertification. So it's like a huge amount of people. So meaning that if we understand a bit more how it works, like 100% means that there are like twice the number of people who are now in desertification places than before. And so 200% is like 3 times. So there are 3 times more people around like deserts in Australia, around this desert here, around here, that are like, so the desert is like growing. In the meantime, we've got less and less wetland, and then drought is not a current, it's more like a sporadic, and you've got the trend is also increasing, but you've got years where there are a lot of droughts and big ones, and years are less. So that's where we found 2 different elements of climate change. One, which is like a long-lasting term changes, which are shaping like slowly but steadily all of the planet. So here we see drought, we see decrease of wetland, and that explains a lot also biodiversity migration, changes in habitats and so on. But they're also like quite maybe easier to prevent, or at least to anticipate, because we know that it's around the places where there was already a desert and so on. But then you've got the other counterpart, or the other part, which is due also to a disturbance of the climate system, and mainly the water cycle, is the drought and all of the other extreme events. Here, well, it's in French, sorry, but that's the number of what we call extreme events. And you see that there is an increase of numbers, so it's like just all together, heat waves, mega fires, bushfires, drought, drowning or like flooding, and all of those extreme natural catastrophes that are attributed to climate change. And we see that it's not like a steady line, but there is still like a huge curve. To me, there is two elements that are quite complex to analyze here. Is that we know that's happening, so we look more and more on it. We've got more and more accurate tools to actually have a look at extreme events, and we've got more and more ways to say, okay, that's an extreme event. So that's a component of like, there's a bias of observation. Maybe that's why there's like a very huge importance here. Before they were like also extreme events, but maybe we didn't pay attention so much, okay? And the other way, it's hard to actually attribute if an extreme event is due to climate change or if it's a natural element of the climate. There are like definitions of extreme events.
Why is that?
Why is that?
Why is that?
Because extreme events, or like meteorological events, and the water cycle and like the, all of the atmospheric circulation and the oceanic circulation, they do have like disturbances anyways, natural disturbances. So basically you've got like a...
But what if you have a natural disturbance in an area where you didn't have a natural disturbance before? So if we had an earthquake, a massive earthquake in this area, would that be always natural, or it's caused due to...
Earthquake won't, earthquake, it's different because... No, I see what you mean. If you have like...
you have a natural disaster in an unexpected place.
Yeah, so that's an element to have an attribution to climate change. So there are like we work quite closely with a team of researchers, like a European team of researchers, and they are actually working on attribution of extreme events, mainly in Europe, but also like other part of the planet, to climate change, and they use artificial intelligence to do so. So they take every like big event that we have in the past few years, and they run simulation, and they check if in any of the simulation they will have this occurrence. Then they say, okay, that's not like due to this current climate change, due to human activity. But if it's like an anomaly in their simulation, then they will say, okay, we can attribute that to climate change. So it's a work in progress. But it's helping as well to prevent more and more, and to be more accurate in preventing the extreme events. But it's not that easy. For instance, there were, and we feel now that every big like meteorological event is due to climate change.
Yes.
But it's not true.
Exactly, that's what I'm trying
Yeah.
But everything that's happening, people think, oh my God, it's because
you
eat too much calories. It's not the case.
No, it's not, but then the proportion of extreme events is nevertheless increasing. It already increased due to climate change, and the prediction due by like the IPCC is doing a lot of prediction. In the projection, there is a component of like increasing intensity and frequency of extreme events. But still, we can't attribute everything to climate change, and there are natural variations. And in the past, in like human history, there are a lot of big like extreme events that have been shaping the history of humanity. For instance, like a huge famine, like huge droughts during the Middle Age had effect as well. But they were caused mainly by volcanic eruptions. So it was, it's all hard, but there's like a trend of increase. That's a map that's showing you, but it's not very interesting. There's anyways a trend of like increasing extreme events. Other part that we're discussing this morning, because water, when it's solid and like in the shape of ice, under a warmer temperature will melt, that's for sure. Then we've got everywhere on the planet a reduction of the ice area in any fall. So here we've got land glaciers at the Kilimanjaro in Africa, and you see here in 1912 and here in 2002, big difference, I would say, between those two, and that the ice that is left in the Kilimanjaro in 2002, which was 20 years ago. So I don't know what's happening now. Yeah, that's possible. And that's the Arctic ice. So Arctic ice is different. You know, we've got two types of ice. Ice that is on the continent, that's fresh water, that is coming from the sun, from the water, from the cloud, and then frozen. High in altitude or high in latitude, so like in the northern pole or southern pole. And then you've got the ice from the water, from the ocean, that is just frozen at the surface. It starts by freezing salty water, but by freezing just reduces the amount of salt in the water, and then the ice of the ice, Arctic ice, like what we call oceanic ice, is also kind of fresh at the end of the day. But anyways, we also see a reduction of its area year after year. And you see like seasonal anomalies, so that's the fact that it's expanding during winter time and reducing during summertime. And you can see that nevertheless, even though we've got sporadic variation, which are like natural variation during the year, and we've got like year after year a small variation, there is nevertheless a trend to decrease year after year the extent of this ice. And the result of it, so the result of one of the examples before, is that we've got increase, steady increase of the sea level, and this is due by the glacier and the ice cap on the continent, but not from the sea ice. The sea ice is already water in the water, right? It's frozen water. If it's defrost, then it doesn't change at all the level of the water, right? That's a very simple experiment to show that with the students. I can show you later. Okay. Well, I think we've got maybe half an hour or something to discuss if you want, because I think we're good with the terrible news that we all know. How do you feel? Not sure about that. I would say yes, hopefully you feel smarter, but yeah, how do you feel? What do you want to?
Right now, Estonia as a country is considering nuclear energy power plants. My home happens to be one of the areas where they're considering to build it. And it's scary. So it's just, it's just don't know. Badlu County in Estonia is the largest county in Estonia, where we have most natural reserves. National reserves, 27% of all the Estonian country. 27% is in our county here, which is preserved rock, but it's like a sword with two edges. If we keep producing these gases more and more, we need to like find alternative ways. But this is just, it's very good to bring knowledge of how to.
Yeah, no, that's the thing. What do you feel by? How do you teach climate change with your students? Do you ever teach it, or do you? Was it useful to do all of that day? Maybe I should have asked earlier. But do you think that is something? Maybe you do already that, or maybe you do better. But yeah, I would love to have some, feedbacks and also feelings about. Well, it's maybe too hard for my students, or it's maybe too
it can generate too much fear to my students and so on. But yeah, if you reflect on what we did today, how do you feel that fit with your needs?
If a student, say we start teaching this climate change, and a student goes in a meeting with all the local municipality government people who say his arguments, that's for real, argument is like, oh, should we have a wind turbine in the forest? That's also a topic right now where I live. And the government officials, the person who has the vote to say yay or nay is saying about the bats, for example. No, don't worry about the bats, don't fly very high. And so there's no knowledge in the people who govern.
Yeah. Yeah.
And that's scary.
Yeah.
So, in my view, to educate young people as much as we can, so that basically we are safe with education.
But for me, I don't know how you feel, but education is not only about the facts and the knowledge, but maybe mainly when we think about climate change, it's about the ability, attitude, and competency that they can have, like a more critical thinking, a better understanding of how science works, to be able to take better decisions. And all of what we did, it's not necessarily the topic that matters more than the process of going through it. I don't know if I'm clear. But I think what we did today is close to what it is actually, what we call inquiry-based pedagogy. And that's some questions we did like a similar training in Mauritius Island, and we had this question at the end. Maybe they're not that important, but they are quite interesting in terms of reflecting on how we conducted this workshop. How did we end up from starting the day with your representation to the end of the day with that drawing there?
It's not all that bad.
Yeah, no, it's not all that bad, but what I'm saying is in the process of knowledge, building the knowledge about climate change, how it works and so on, was it descending, or was it trying to share it with the others, or how was it? And if you were in my place, or as a teacher, how would you conduct such?
I think it was fun to kind of do the experiments and do some playing around.
Yeah.
It was fun learning.
Okay.
Which was much more funner than just to look at some slides and hearing you speak, and it was much more fun.
And do you think that's doable in classrooms?
I think it's very important.
Yeah.
So they can participate and they can kind of investigate themselves and compare the data that they will have from some experience that they are doing together.
Yeah.
That's, I think that's good feedback.
And as a teacher, how would you, what's your role in that process of teaching?
You kind of, you kind of help them.
Yeah.
Not to just tell them what to do, but guide them through.
Yeah, facilitating, guiding, and so on. I think we did it fast, because it's only one day, but you can conduct this type of experiment, more step by step, slower. You can also have differentiation with different levels of students, if your classroom have different levels and so on. So there are some elements of
active pedagogy, as we say, that are like quite nice to have it. And
this kind of, let's say, this kind of lesson, you start doing this lesson, you yourself as a teacher need to be really properly prepared.
Yeah.
Because debriefing, say if you do a game, debriefing needs to take as much time as the game.
Definitely, definitely.
So in order to sort of like make sense of what you did, we don't go out to play just to have a game, but there's a point to the game. So debriefing is very, and briefing, game debriefing is very important too.
Yeah.
Because then that's where the cognitive change takes place in the head. Why did we do it? So that's good.
No, definitely. I think that's very important. We're going to talk more about gamification and gamification tomorrow. But I think that, pointing out that we need time to debrief, we need time to have this like, okay, what did we do all day long? Doing like a schematic like representation of it. It's possible tomorrow we can have like a refresh on what we did the day before. So all of these little tips is very useful to structure the knowledge, but also like put it down in the head. But the phases of like playing, but also experimenting, investigating is very important. And having this feeling of, okay, it's hard as a, and I think I'm still learning, but as a trainer, like I'm always a bit like scared when the teachers are lost in where I want them to go, right? There's this feeling as a teacher of like, okay, I don't want to give all the answers, but then I don't want them to be lost and to feel like, frustrated because they don't understand where I want to go. So there's a fine line between. I think there's a fine line between like setting up objectives, but then having that space where it's normal to be lost, and that's where creativity, curiosity, and so on is aroused, and that's where knowledge can be like strongly built up because it comes from cooperation between students, it comes from their own findings and so on, and you need anyways debrief, and you need, so it's not that simple, and and I think that's where, one type of pedagogy where that's useful for science, but also useful for critical thinking and so on.
In Estonia,